Okay, I see we're live. Hello, everybody. Welcome to GRCon 20. I'm super excited to be doing this. Obviously, would rather be in person, but very excited that we were able to pull this together, and I think we're going to have a really great week. So with that, let's go ahead and get rolling. Let's pull up. Can I pull up my slides? All right, fantastic. So this is going to be a little bit of a mix of welcome to virtual GRCon and how is this going to work, and also my usual project update and what has happened in the last year since GRCon 19. So first, code of conduct. We of course rigorously enforce this. This is never not in place, but especially during GRCon with so many people interacting and participating within the community. If you need to report anything at all, feel free to message any of the staff or officers in chat. Also, this email alias is monitored constantly. So our code of conduct does apply to absolutely everywhere that GNU Radio exists or our community is active. And if you have any questions about that, please feel free to ask. So with that, I'd first like to make sure everyone's aware that there is a participants guide for the virtual conference. This has links for everything that you could need. If you haven't gotten this yet, if everyone who registered for the conference should have gotten an email late last week that had this. If you missed it for some reason, you can find a link to it on the GRCon website. Make sure you go grab it. It has details on how to sign up for chat, what the schedules are, how our virtual expo booths are working, everything like that. So make sure you go and grab it. Once you are in the chat, if you head over to the GRCon announcements channel, you can pull up this page, and there's a list of, I've cropped it off here, but there's a list of all the different channels that are active in the chat for GRCon. And there's channels for discussing talks as they're going, the workshops, our sponsors, asking for help. So make sure to join the ones that you're interested in. And I'm looking forward to an active discussion as the conference moves on, especially around the CTF. So as of the start of this talk, the CTF is live. The first place to start is definitely by joining the chat channel. You can also head to grcon-ctf.online. To get rolling. A few things I want to call out. As usual, donated challenges are welcome, and you do score additional points for donating challenges that are accepted. This year, there is a storyline, and I am not privy to it. I'm actually very excited to see where it goes. The challenge server will remain up after the event, and for anyone who wants to understand how the challenges were created, all those flow graphs will be released after the event. All right, so with that, I'm going to kick off the rest of my deck with my usual chart. Kind of grief the community for griefing us. So as many of you know who've attended GRCons in the past, our community has a ongoing record, bad habit, not sure what the right word is, of waiting until the very last minute to register for the conference. And some years ago, I would have some pretty serious palpitations over that when I was worried about the solvency of the project because we were trying to pay conference bills and nobody was registering. Not so much the case anymore, but even when there was a free conference, all of you waited until almost the very last minute to register. You can see that these are all zero registrations for quite a while, and then the huge spike just in the last 2 weeks. Even when it's free, we follow the same pattern. But I'm super excited for everyone that's here. So a couple of major announcements from the past year. 3.8 finally released. So huge thank you to Marcus and all the other officers who worked so hard on pulling it together. And of course, everyone who contributed. The contributor list was massive. It was absolutely huge. And 381 RC1 is currently available. So I want to call out that not only did we have 2 releases of Volk. So I know we have a lot of people that are listening to this that are new to GNU Radio, who haven't attended GRCon before, if you're not familiar with Volk, Volk stands for the vector optimized library of kernels. It's a library of SIMD math operations to speed up, in our case, DSP, but lots of different things. And it's a sub project under the GNU Radio umbrella. So as of this year, we have 2 new maintainers for Volk, Johannes Demmel and Michael Dickens. And we've had 2 releases of Volk, 2.10 and 2.20. So our stats here added another year. As you can see, we've continued to grow in both closed PRs and issues, which I'm super excited about. We do have, someone pointed out on Twitter a week ago that there are a lot of outstanding PRs and issues as usual, but if you look at the activity, it actually we're doing pretty good on these, and the number filed and the number closed continues to go up, which I'm super excited about. So this is the 10th year of GRCon, which is pretty incredible. The first GRCon was hosted at the University of Pennsylvania in a small classroom. Technically, I think Fire Code said that the max number of people in that classroom was 40. So we definitely only had 40 people in that classroom. Yeah, GRCon has obviously grown substantially, but it has become something that I think the community should be really proud of. After Philadelphia, we went to Atlanta and then Boston and then DC. DC was the only city we doubled up on. And then somewhere around that point is when we started selling out GRCon. So Boulder at University of Colorado, 250, and San Diego, and then Henderson, which is right outside of Las Vegas. So this year, we hit 344 paid registrations for GRCon. So basically matching what we saw at Henderson last year. But in total, we've had over 1,400 registrations. So obviously, totally understandably, being virtual has made it much easier for people to attend, but we've also had a lot more participants. So I think this is this will be an interesting takeaway for virtual conferences and the accessibility they provide to the community. So I do want to highlight that we've had hundreds of talks over the last 10 years of this conference. All of the ones that have been recorded. We started recording in 2012. Almost all of them are on YouTube. Slides are often available, not always, but most of the time. And this is our 4th year of the GRCon Capture the Flag Challenge. So this year, as always, this conference is only possible because of sponsors. I especially want to highlight the 3 companies up on top, Analog Devices, Epic, and Ettus. They've been the longest running sponsors of this conference. Basically, since we had sponsors, these companies have supported the project. And then I want to shout out to CNF, SETI, and Xilinx for joining them at a top tier. And I'm really excited about the other new companies that we have coming in and sponsoring the conference. This is another year that Perspectives joined us, but also Raytheon and Sandia, who've made some substantial code contributions in the last couple of years, and Syncopated. And then Ryan and Aaron, and our Microwave Journal is our publication sponsor. So GRCon only happens because, and actually before we come off of this slide, I should highlight a lot of our sponsors have chat rooms in the chat, and if you're interested in talking to them about your products and services or jobs, what they're doing, please go talk to them. We're like many other conferences, giving the running virtual expos, and there's actually a lot that's really kind of cool about running virtual expos. So we're excited to give it a go. And a lot of these companies are excited to talk to people. And all right. So I know I say this every year, but I really, really want to try to hammer it home. Putting together GRCon is an absolutely tremendous undertaking. It's hard to really describe how constant it is. And I should say, some years ago, it was mostly me, and then we had a team, and I was really almost completely uninvolved with the organization of the conference this year. And Michelle and Derek and Sam especially really, really carried this. It's constant. It's every day, and it's hundreds and hundreds of hours from everybody involved. And this conference is going to end, and a couple weeks later, they're going to be working on next year. So a huge thank you to Michelle, Derek, and Sam especially. Also to Neil and Steve Croft for helping put this together. I also want to highlight Confreaks and Cindy, who are actually making this possible. So as you might imagine, there are some there's some skills and knowledge in hosting a completely virtual conference, and Confreaks is making it possible for us. And they've really, Cindy has really gone out of the way to help us set this up. So a huge thank you to Cindy. This is also the 5th year of our technical proceedings. So as of the start of this talk, the technical proceedings have been published. I somehow forgot to put the URL on this slide. It's pubs, P-U-B-S, .GNURadio.org. We have got a number of papers that have been published in the proceedings this year. They are awesome. I want to highlight our technical proceedings chair, Tim O'Shea, for once again continuing to make this happen. He's been the chair every year. And also to Michelle, again, for helping put this, making the proceedings possible. So our partners over in the EU unfortunately had to cancel the European GNU Radio Days this year because of COVID, but we are expecting an announcement later this year about 2021, which we're super excited about. So if you haven't gotten a chance to attend the EU GNU Radio Days and you're able to get to France for it, I highly, highly recommend it. It's doubled in size over the year, each year, and they have fantastic content. And if you can't make it, of course, content is available online. But it's a little bit of a sister conference, and it's a great, great group. Also want to highlight that the SDR Academy, which is not organized by GNU Radio leadership, but is we typically are involved, and GNU Radio is a major center point of their content. So they moved online because of COVID, and as a result, the submissions grew so much that they actually ended up adding a second full day of content. So if you missed their talks, you can find them. You can find them online. They've got some really, really interesting ones this year, including a couple on like machine learning in RF and real-time processing. So if you don't follow the SDR Academy, I recommend checking them out. So this year, as usual, we had a pre-FOSDEM Hackfest. So, and I'll talk a little bit more about FOSDEM in a second. But this year, the Hackfest was hosted at the European Space Agency at their ESTIC facility in the Netherlands. And we had 14 participants go with a number of topics. So if you've never attended a GNU Radio Hackfest, they're lots of fun and a fantastic opportunity to get more involved in the project and spend time working on something that you're interested in or that you want to see, you want to dedicate some development time to, and you'd like to do it around other people that are also focused on hacking on GNU Radio. They're also an opportunity for people to actually sit down in person and whiteboard and hammer through problems and do project planning and that sort of thing. So they're really important events for the community, and we were really excited to be able to do this at the ESA this year. Thanks to one of our officers, Andre Rode, who actually works there. So FOSDEM, we had another great year of the Free Software Radio Dev Room. So these are GNU Radio leadership is typically involved with helping organize this, and we had another really successful year. So if you're not familiar with FOSDEM, FOSDEM is the Free and Open Source Developers Meeting. It is hands down the largest conference of free and open source developers in the world. It takes place over 2 days in Brussels in February of every year. And it's absolutely massive. It's just absolutely massive. But it's an amazing place to go and meet people who are working in open source, tangent that aren't working directly on your project, perhaps, but are working alongside it or tangentially to it, or even other projects you've never thought about getting involved in. Right, every major open source project you can think of is active at FOSDEM. Right, from KDE and GNOME and VLC to the Linux kernel itself. So FOSDEM is really, really good about having all videos recorded, and it's actually live streamed. So I'm not sure what's going to happen to FOSDEM next year. I don't know if they've made an announcement about that. But if you haven't been paying attention to FOSDEM content, you should absolutely check out the content from this year and previous years in the Free Software Radio Dev Room, and check out some of the other rooms. They've got really, really great stuff. So looking back on some of the other things that we've done this year, we once again participated in the Google Summer of Code. So this year we had one student who developed digital predistortion, GRDPD. So this is super, super cool work. And he produced a number of really awesome blocks that are available. So it's very well documented, and the process by which he went about it is described in detail in his blog, which you can check out. It's also linked. His blog is linked to from his modules homepage. But if you're interested in all at DPD, or you're working with amplifiers, or you need to do something like that in your own radio systems, be sure to go check it out. So as many of you have probably seen, one of our biggest changes this year is we dropped Slack and we moved to Matrix. So it was when we adopted it, it was originally called Riot or Riot Web. It's now called Element. And it's what everyone is using now for conference chat. So we've been talking about this move for a while. We introduced Slack a few years ago as a way to make it easier for people to get involved and communicate with the project. And we had some issues with Slack, notably its price, which we were on the free tier, but the free tier has a number of limitations that were causing us issues. It's also not open source. The data transparency wasn't great. IRC bridging was painful. So we looked at a number of different options and settled on Matrix. So there's a number of pretty exciting things about Matrix. We're still working through how best to use it, but it's working pretty well for us at this point. One interesting thing about it is it's used really broadly across the open source world. I've got a few examples here: KDE, GNOME, the Wikimedia Foundation, even the French government uses it, and it makes it possible for you to interact with those communities from your one account, from a single account location, right? So you don't have the problem of needing a dozen different accounts for dozen different projects. If you're interested in some more detailed discussion about why we chose Matrix and why we dropped Slack, there's a blog post on GNU.org about it. If you're having any problems, let us know. But we're really excited about this. Chat is super important for making the community more accessible and inclusive. There was a time when IRC was the one true way of working with open source communities, but IRC is difficult for a lot of people for a lot of reasons. And having modes of communication like Matrix are really important for the project. So we're excited about this. And feel free to reach out if you have any questions. You want to start your own room, you're having trouble or anything like that. So start talking about some of the development that we've got going on, some of the things that have happened in the last year. I'll start with GNU Radio, what we call GNU Radio 4.0. So this was a major topic that we highlighted at last year's conference. So by 4.0, the moniker 4.0 at this point has really come to mean basically replacing the core GNU Radio runtime, the scheduler. So the scheduler as it exists today, with mostly as it exists today, was conceived of and written when GNU Radio was first created in 2001. And when it was written in 2001, it wasn't multi-threaded, and it had some other limitations. And those have since obviously been added to it. But fundamentally, it's architected in the same way. And the world of, not just the world of radio, but the world of processing, and especially embedded processing, has obviously completely changed in 20 years. And it's very, very clear that heterogeneous processing topologies and distributed platforms, right, are the future, and it's where we need to be. So, it's just can't just modify the existing scheduler and make it good at that. So one of the major, probably the primary technical thrust in terms of core GNU Radio development right now is, okay, what does that look like, and how do we do it well? So we've got a number of officers who are dedicated to this. Josh Mormon especially, I'll call out, but also Bastian and Marcus. And there's a number of DARPA programs that have worked on problems in processing. And so this company, Blacklinks, is currently working on basically taking some of those concepts and studying and analyzing and prototyping and implementing, taking those concepts and developments and bringing them into GNU Radio. I'll also take a second and call out a lot of the work that OpenCPI has done and is doing is fundamentally about scheduling and resource allocation and applying, mapping processing blocks over topologies. And OpenCPI has, CNF Technologies is a sponsor of the conference, and OpenCPI has a number of talks and workshops this week. So there's a lot going on in this space, and as a project, we need to figure out what is the best way forward, and how does that get implemented. But this is something I'm especially excited about. I'm super, super excited about really the next generation from a technical perspective of GNU Radio. So to highlight something that is not core GNU Radio development, but one of my favorite out-of-tree modules is GR satellites. So Daniel has a talk on GR satellites. So I don't want to steal his thunder, but I just want to highlight something just to give you some idea of how amazing GR satellites is these days. It's now at the point where you can write a config file, like what you see here on the left, that describes a satellite and some aspects about its communications link. Run a quick command line program from GR satellites and get decoded packets. If you think about everything that has to happen behind the hood to make this kind of thing possible, where you can describe in very simple metadata what a satellite is, and then say, here's a capture, what's in it, and have it go off and do that for you. That's incredible. So GR satellites is easily one of my favorite out-of-tree modules, and I'm super excited to see Daniel's talk. And if you're not familiar with GR satellites, you should absolutely go look it up, because people are doing incredible things with it. So another awesome development this year was GNU Radio on Android. So Tom Rondeau, the previous lead of GNU Radio prior to me, had done some GNU Radio on Android work back in 2013, 14 kind of time frame, I think. Might have even been a little bit earlier. And there were a number of people who had taken that and built on it. But there wasn't anything that had been super recent, and certainly not with GNU Radio 3.8. So in case you missed it, Bastian has published a bunch of new GNU Radio on Android work. That's amazing. It does support 3.8. It supports a bunch of front ends. It doesn't require rooting the device. All the signal processing is in C++. And it has a lot of support for a lot of the GNU Radio tools you're used to using, even Volk. So if you didn't see this, you should absolutely go check it out. It's really, really amazing work. And it is also super exciting just from the perspective of being able to walk around with your cell phone and a RTL SDR. So I also want to call out Metasat. So for anyone who watched or was at the conference or watched the talks from last year at GRCon, we had a presentation about Metasat. So this is a collaboration between the Harvard Smithsonian Center for Astrophysics and the LibreSpace Foundation. This is funded by the Sloan Foundation. And they've built out the Metasat schema for small sats. So this is super, super cool. And if you start to think about the types of insight that you can gather with fully described satellite missions, there's some really, really interesting problems and analysis that you can do. And so this is happening, entirely open. It's all open source. If you work in small sat space at all, or at all interested in metadata for radio systems, you should check it out. It's a really cool development. So on that note, I gotta rib myself a little bit here for SIGMF. So there have been some amazing SIGMF developments. I've got a few here. So on the left is this is a GUI tool that Aerospace Corporation has developed for working with SIGMF. Bottom right, many of you will recognize this as InSpectrum. There is actually, I don't think this has been merged yet, but there's now SIGMF support filed for InSpectrum. LibSIGMF, which is a library, C++ library for working with SIGMF, created by Nathan West. And so SIGMF continues to explode in usage. I have to say I am the lead maintainer of SIGMF, and I am delinquent in addressing PRs and issues. So for that, I apologize. And I've never felt more aware of that. I was in a workshop a few weeks ago, and it was an academic workshop, and almost every single professor that presented was using SIGMF. I've never been more aware of not having addressed open PRs. But SIGMF is continuing to grow and expand, and there's lots of people doing amazing things with it. Even if you haven't seen repository activity, I really am I'm actually already working on coming back around and addressing some of those PRs. So there's a couple of highlights I want to call out in sort of pop culture. So this year we've got two. The first is Mr. Robot. So in season 4, episode 4, you can see this screen. Now here you probably recognize Audacity on the left, right? Another open source tool, but for working with audio. And then here you can probably see GQRX. And then in episode 9, we've got HackRF, which is very cool. And then my second one is in HBO's Silicon Valley. So this was the very last episode, I think. Episode 7, season 6, I think it's last episode. It might be second to last. I think it's last episode, though. They've got HackRF and GQRX, and the climactic scene that closes the storyline is SDR and GNU Radio, GQRX, HackRF. So I thought that was super cool. So now I'm going to start sharing some of my favorite tweets from the last year. So I'm going to start with this one. So the 780th Military Intelligence Brigade with the U.S. Army tweeted out this picture. And if you look very closely at their monitor, you can very clearly see a GNU Radio flow graph, and GRC did so. So we actually had some interaction with Twitter, over Twitter, with whoever is running this account. And apparently what had happened was, the PR team come in and said, we want to share a picture of your team doing work. We really want to highlight open source. Pull up your favorite open source project. And GNU Radio is what came up. So this one from Mike Walters. So Mike is the creator and maintainer of InSpectrum, who I just mentioned before. So this is Mike simulating a FMD mod using CXX-RTL. So if you're not familiar with CXX-RTL, it is a simulation backend for Yosis, which is a completely free tool chain for doing programmable logic. So think FPGAs. Now this is really, really cool because what he's done is he's written, actually I'm not sure if it's, I assume it's Verilog, I suppose it could be VHDL. But he's written HDL for an FPGA, simulated it using the CXX RTL backend from GNU Radio, and then taken that programmable logic configuration and deployed it in real hardware, and it worked. So this is really, really cool, entirely with open source software. Next, I want to highlight some work that Clayton Smith did. So Clayton Smith organized the CTF for B-Sides Ottawa. And for that, one of the things he did was he built a frequency hopping challenge. And you can see here, right, the frequency hopper in the spectrum. So if you're interested in either, I should say, this is not a clue for this year's CTF. This is I think it's just cool. If you're interested in how Clayton put together the frequency hopping flag and what the solution was to receive it, you can check out this blog post that he has, and it walks through it in some detail. And by the way, all the slides are going to be available. So I was very careful to put links to everything in all of these slides. So if there's anything here that you particularly want to go check out, you can grab the slides as soon as they're published and then just click the link. Shout out to Kate Timken, who made a standalone distribution for GNU Radio on macOS. So for a long time, your two options for using GNU Radio on macOS were either basically building it from source yourself, which can be painful, or using the MacPorts packages that have been maintained by Michael Dickens. So this was another option, and a lot of people had immediate success with it. So if you don't follow Kate and you're on macOS, you should check this out. On the same note, Kate and Mike Osman built a really cool demo that uses the Great Scott Gadget's Great FET device along with GNU Radio to mess with the output of a toy guitar. So we've seen a number of uses of GNU Radio for doing fun things, especially when it comes to signal processing for audio and music and instruments. Most notably, I think the first was from Juha Viernen back in like 2012. But this is super cool. They demoed this at the SuperCon. And if you're interested in checking it out, you should go look at it. And you can pull up the flow graphs and play with it yourself. You swap out device blocks for audio files and that kind of thing. So just a little bit of a teaser. So there is a talk this week on the ESA OPSAT mission. You can absolutely check it out. When it first went live, there were a number of people who were active in organizing, getting the ESAs, or spreading awareness of what was going on, getting GNU Radio flow graphs and applications out. I'm here highlighting Chris Bridges. But this was super, super cool. And if you haven't been following this, you should wait to see the talk and then dive into it. But I think this is a really amazing use of GNU Radio for, really citizen science. So next, this is really cool. So this is from Mike Piscopo, whom some of you might know as GoStop14. So Mike is the person who published, like, for anyone who's doing anything in the GPU with GNU Radio, you're probably benefiting from some of the work that Mike has done. So he published Sparrow Wi-Fi, which is an analysis tool for Wi-Fi, Bluetooth, drones, a bunch more, because there's a bunch of different tools and analysis utilities within it. So if you missed this and you in any way work in cybersecurity or with 802.11 devices, it's worth checking out. So next, I want to highlight the Marmot E modem. So Marmot E was the team from Vanderbilt University that participated in DARPA's Spectrum Grand Challenge. They won second place. And they did all of their work in GNU Radio. So they have released their modem as an out-of-tree module, Marmot E, which you can go and grab. So they've released everything that they've done as GPL v3. I think there's only a couple of things that they did not release. One was, if you're not familiar with the Spectrum Grand Challenge, it was the goal of it was to build radios that autonomously moved around in the spectrum. And so they did not release the decision engine that was deciding how to move around in the spectrum. Right? So the AI component they didn't release, and they also didn't release some of their couple of the logging utilities. But I know there's a note on their website that says if you're interested in those things, reach out to them. But the physical layer itself is totally available and very well documented. So if this is something that's interesting to you, you can grab it at marmot.io. Okay. So this one was pretty recent. I saw this just last week, which is an Aqua mod. So Aqua is a NASA Earth science satellite mission, and sort of fortunately the most recent imagery is of all the fires on the west coast of the U.S. But this was a new satellite that we hadn't previously seen someone build a receiver for in GNU, or at least publicly. So that's now available if you're interested in tracking that. So this next one is actually not GNU Radio based, but it's so cool I couldn't help but include it. So this is a completely open source implementation of 802.11, or Wi-Fi specifically, implemented in programmable logic that works with the Linux Mac layer. And you can see that it's heavily right now targeting Xilinx and ADI dev boards. And you can see their dev board support. And so this was presented at FOSDEM. You can also, so if you're interested in seeing a talk about this, go to the FOSDEM Free Software Radio Dev Room from this year, and you can see a presentation on it. But this is really amazing. There's been a lot of 802.11 work in GNU Radio. I think as anyone knows who's tried to do that, right? In order to build a fully operational Wi-Fi transceiver, that you need to be in, and you want to do it in software radio. You need to do it in programmable logic, right? At least with the current radio scheduler design, doing it all in software doesn't work. So this is an example of developing this in programmable logic, and it is very, very cool. And you can see the ping times here, which are mind-blowingly fast. So the last one, I've never highlighted one of my own tweets before, but I'm going to do it here. So I got the Windows subsystem for Linux 2 update on Windows 10 and did an apt-get install of GNU Radio, and it worked first try out of the box, which is amazing. I highlighting this because I'm very, very hopeful that it leads to easier packaging and use of GNU Radio on Windows. Now, I will say that trying to do anything beyond what I'm doing here, which was just basic simulation, like in order to use a USB device, for example, you have to build your own kernel and do a whole bunch of behind the scenes magic. So there's a little bit of a ways to go. But for anyone who's interested in using GNU Radio on Windows, isn't scared of diving into the trenches a little bit, this is probably worth checking out. So I also want to call out this work from Alex with his Ionisand, which is really, really cool. So this is actually a picture from Antarctica. And I think this is the first known use of GNU Radio on Antarctica. I could be wrong about that, but this report provides lots and lots of interesting details about how they built a very low cost Ionisand and deployed it into the Antarctica using GNU Radio and low cost COTS general purpose SDR that everyone's familiar with. So next, I want to talk a little bit about SETI. So as I'm sure many of you saw, we recently, and by recently I mean last Tuesday, announced that we've formalized a partnership with the SETI Institute. So this is a really, really big deal for, I won't speak for SETI. I think it's a really, really big deal for us, us being GNU Radio. So I'm going to talk a little bit about why we did this and why we're so excited about it. First, I'll tell you a little bit more about SETI. So, everyone kind of thinks of SETI, I think, as the people who are trying to detect intelligent life in the universe. The SETI Institute is actually pretty broad in its scientific pursuits, right? So, at least, especially in the RF world, right, we typically think of what's all on the far right side here, right? Radio SETI, right? But there's lots of different areas of science and research that fall under the SETI Institute umbrella, from astrobiology to actual working with NASA on satellite missions. They've got they're partnered with NASA on a number of missions, and we've also got through the Breakthrough Listen project a pretty incredible group of radio telescopes that are all affiliated and working on the effort. They're also already working with quite a number of companies and funding agencies that we also have very strong relationships with. So it's kind of I want to talk about why we did this. So actually, first, why did we pick SETI? There was a lot of groups that we could have partnered with to help grow the project, but there's a few things in particular about SETI that made them an outstanding partner for us. So first is they really share a lot of common objectives, and we value a lot of the same things, using the royal we here, but they are very driven to making science open and accessible. And a natural part of that is a huge focus on education. And there, I mean, not just education in terms of, so like STEM outreach, for example, right? Like working with middle and high school students and making topics in science and engineering accessible to them, but also advanced studies, so like research, intern research programs and graduate research programs and those sorts of things. And they're willing to chase. So, I mean, obviously they're trying to detect intelligent life, but even if we're not interested in detecting intelligent life, partnering with a group that isn't scared of going after the really big, hard problems and doing it in a way that is really innovative and focused on just getting stuff done is super powerful. But really what it comes down to is, fundamentally, as we've been working with them over the last 2 years, it became really clear that together we could do some really, really amazing things. And whether we're talking about making advances in STEM outreach and science and the use of open source radio in scientific research and education, to making available SETI radio telescopes to the radio community. There's all kinds of really, really amazing opportunity here. And I think that kind of comes to my next topic, which is the radio organization itself. So there is a talk. Martin is going to be giving a talk about this on Wednesday morning. So this first thing Wednesday, if you are all interested in how the GNU Radio project is growing and what things are going to look like going forward, you should absolutely be sure to catch this. So just to set a little bit of context, GNU Radio is currently run by me. So I am, in open source terminology, known as the benevolent dictator. And the truth is we've long outgrown this form of governance, right? Our GNU leadership should reflect the community, and our governance should reflect the impact that GNU Radio has and the impact that our decisions have, right? So, if when I or GNU Radio leadership makes a decision, it can have really substantial effects through the scientific research industry, all the different sub areas that are part of GNU Radio, and our governance model should be inclusive of those perspectives and opinions, and should be appropriate for this type of resources and magnitude of the decisions that we're making. And it's not, right? So me making those decisions unilaterally is not good for the organization. So we are moving to a more community-driven governance system, which means that I will, once this is, once we have this well-defined, I will be handing the torch over from, as a one-person benevolent dictator who's delegated really at this point almost everything to the officers who actually are keeping GNU Radio running, to a community-driven governance system. So we're not quite ready to do it yet. The governance model is still a little bit under development. So the details of what this is going to look like are what Martin's going to discuss. So if you're at all interested in getting involved, please jump into that. And one of the major things that I want to highlight here is the way that we work currently, the way that GNU Radio has always worked, is in the model we're in, you become a core leader or an officer right now when I say it happens, which is that's a problem, because there's no path for someone newly joining the community to become part of leadership, right? That doesn't involve me. And there absolutely needs to be a way for someone who's joining the community who wants to become part of leadership and who wants to be actively contributing to the project at a really broad level, right? To know how that happens and to see a path to getting there and becoming part of the leadership circle. So that's one of my absolute major goals here, is to make the leadership, or make becoming part of running GNU Radio, available to people who want to get involved, and make it clear and transparent how they do that. So that's kind of a segue to my last topic, and then I'm gonna try to take some questions. So every year I take a few minutes at the end of my talk to soapbox on something, right? So this year, what I'm going to soapbox on is the gap in understanding how to work with open source. And so let me expand what I mean on that a little bit. So, open source it's really, I'm not sure language is the right word, maybe mechanism. It's becoming the language or mechanism of scientific pursuit. And I mean, in a lot of technology spaces, it already is the de facto standard way of technical development, right? But that's spreading too. We're talking about code, data, and so data might be from the perspective of, like, now we all think of machine learning, right? But it could also be reproducing someone else's scientific research, right? Development of open standards and interfaces. We see this especially in 5G, right? Shared common resources. So these could be common tooling that we all use to common mechanisms, for example, citing someone else's work. Even open governance models. Open publications. I should have included that, right? I mean, everywhere you look, open source is becoming the way stuff gets done, right? And it's becoming the way that it's becoming the de facto starting point, and then the way that things are developed and built on. And one of the things that's become super clear to me in all of the work that I've done in working with outside groups, and by outside I mean groups outside of the GNU Radio community, is we're no longer 10 years ago, or even when when GNU Radio started, we were heavily fighting the battle of yes, open source is good and a useful thing, and here are all the benefits, right? And eventually open source won, right? And then it became here's why you should be doing open source software radio, right? And now what we see is open source software radio is the way many people are doing things, but even in those areas where it's already being adopted or open source has already been embraced, there's often huge gaps in understanding how do you actually interact with it and participate in it. And sometimes it's technical. So to give you an example, actually the workshop that I mentioned previously a couple of weeks back, someone said, we'd done all this development and we published our code on GitHub, but it was never upstreamed. And if you think about that for a second, like, yes, I mean, like if you're familiar with the way open source works, yes, obviously just making your code public isn't the same as trying to upstream it, right? Just putting your code on a website doesn't mean it's going to be included in a project. There's a lot that got missed there. To legal mechanisms, right? I mean, the way open source works right now is it kind of requires everyone involved to be a little bit of an armchair lawyer and understand IP law, sometimes international IP law, which is a huge barrier to entry. And then there's understanding how to work with the community itself and how to be a part of it. There's numerous examples, and we see this in GNU Radio sometimes, where a group will go and spend 2 years developing some new incredible capability, and then sort of show up and open source it and ask that we merge it. Like that doesn't work, right? That's not how you can't interact with the community like that. That fundamentally is not productive, and it, especially given that open source, or the people who benefit most from open source are those that are active in the community and understand how to benefit from it, right? That's a huge problem. And in a lot of cases, this falls out of people wanting to participate in open source who are not software people, right? And this is especially prevalent in GNU Radio, right? So you see this, for example, in a DSP engineer who really just wants to do DSP. GNU Radio is the way you start doing DSP in a lot of places now. And they don't know software, they don't know Linux, they don't know Git, right? And they certainly don't know how to interact with an open source community. So this can be a huge barrier to people. And even once they get past that barrier, it prevents them from benefiting as much as they could from open source. And it prevents GNU Radio from benefiting from the contributions that they could make. So, GNU Radio community is super unique. There's not a lot of open source communities that have the mixture of people that we have, mixture of people in organizations, right? With academics and hobbyists, government, industry, vendors, right? With all of the sponsors that are part of GRCon, for example, ham radio enthusiasts who sort of include as their own demographic. We've created a really thriving and healthy community, and we've learned a lot about how to do that in the process. But bridging that gap and figuring out, how do we make not just SDR accessible, but how do we make open source more inclusive and lower the barrier to entry to that? I think is a really, really important problem, not just for GNU Radio, but frankly for scientific pursuit and government and everything else. But GNU Radio is pretty uniquely situated to provide the lessons that we've learned and try new things and try to improve it. So I will stop there. I think I have only 4 minutes for questions. I meant to leave more. But yeah, so I'll stop and say I'm super, super excited for this week's GRCon. I'm excited to chat with everybody online. And with that, I am going to come out of slides and take a look at some questions that we've got. All right, I see first a note to say, let everyone know, yes, we know that the chat is extremely slow right now. We've notified the company that's hosting it, and all right, so this should get settled and fixed. Either once the inrush of new participants relaxes or the hosting company gets to us. Next, people complained about Ben erasing Huntsville from the map. I did erase Huntsville from the map. I totally forgot to add it in the table. I am sorry. Thank you for whoever called that out. I'm sure it was Michelle. Thank you, Michelle. I can't believe I forgot that from the table. Yes, Marcus, you're right. It is 382. I should have updated that slide. We're at Volk 2.3. EU GNU Radio Days will have a flyer available online during this conference. Oh, cool. I didn't know that. So that's awesome. So during the breaks, you'll see a flyer from EU GNU Radio Days on regarding announcements. Oh, I didn't know this either. So Ryan Voles has GNU Radio installers for Windows via Anaconda. Okay, cool. If there's any more details on how to grab those installers for Windows for GNU Radio from Anaconda, if someone could share them in the chat, that would be great. And Eric Blossom asks, what is SIGMF? Hi, Eric. For anyone who doesn't know Eric was the creator of GNU Radio. Eric, SIGMF is the signal metadata format. It's a way of describing digital recordings of analog data in a way that explains both how to make sense of the data and then to describe processing and aspects and characteristics of the data itself. Okay, so there's 2 minutes left. Without further questions, then I will return the 2 minutes to the conference organizers and stop there.
a hacker of signals. Oona is interested in radio, digital signal processing, sounds, visualizations, mysteries, music and sound art, and vintage technology. Please welcome our keynote speaker, Oona Räisänen.
Hi and welcome. We'll take a look at decoding analog video with an SDR. This talk is sort of a story. I'll tell you two related signal discovery stories from my own personal perspective. How I discovered a mysterious video signal and decoded it and then used this solution to later build a color PAL decoder. I like to tell stories like this in the hopes that I would inspire other people to deep dive into signals like this. And maybe, since I'm not very versed in GNU Radio, maybe someone gets inspired to build a GNU Radio solution. There will be some implementation details. I'm not getting mathematical, but I will get somewhat technical in this talk. My name is Oona. I work as a C++ programmer, and sometimes I even engage in Perl witchery on the side. And on my free time, I like to do anything related to DSP or signals. So I spend a lot of time listening, analyzing, researching. I like mysteries, especially. Anything can be a mystery. Any sound that I hear or radio signals that I receive. And I write about these mysteries in my blog. And this is my face. Hi, I'm awkward. Some background for this talk. About a year ago, I was listening to PMR 446 a lot, which is a European UHF band for walkie-talkies. I used my AirSpy R2, which has been my favorite receiver for quite some time. And in one place, I kept noticing this weird wideband interference signal on top of the band. It was very wide and it was very obnoxious. It completely blocked all the PMR channels. So I really had to find out the source of the signal because it hindered my fun activities. I had to find out if it's something that originates in my setup or if it's something in the vicinity so that I couldn't use that particular very nice QTH anymore. This is what the interference signal looks like in GQRX. This is just a small part of it. It spans a lot more frequencies. So it consists of very narrow and strong peaks that are all over the band. I listened to the signal by treating it as AM, and it sounded like video. Now, I'll explain what I mean. When I was a child, I used to play the 8-bit NES a lot, and the NES has a video output and an audio output, but the outputs are using a similar kind of plug. So it's very easy to mistake the video output for the audio output. So I would often accidentally plug the audio cord to the video socket and hear the video signal, the vertical synchronization buzzing, which is 50 Hertz here in Europe. And this interference signal sounded a lot like the NES video signal. Let's hear it. But why would there be a video signal, such a strong video signal, and such a wideband one here? That was a mystery to me. I had some suspicions, but I had to test this out. So I went through a lot of monitor display modes, so just common display modes, and tried to get the timings right so that I would get some kind of a picture. I could see if the signal makes sense as a video signal. So what I would do, I would take each sample from the radio at 10 megasamples per second, and I would take the amplitude of the IQ sample and just simply use it as the brightness of a pixel in an image. And then I would position the pixels so that it would be synchronized with that the vertical synchronization would always be at the same place. And this is what I got. The vertical synchronization signal is at the top, and on the left is something that appears to be a horizontal one, and the rest should be video, but it always seemed to be blank. But I noticed that the center frequency of the interference happened to be an integer multiple of the pixel clock of this display mode. So I kept trying the other multiples at other frequencies, and indeed I found some frequencies with video signals. I came home and I tested this with my own monitor at home. And here's my test setup. ST AirSpy R2. I use a small whip antenna, or the telescopic antenna of the R2. I have the display very close to the radio, and I wrote this program that automatically synchronizes the image and displays the brightnesses and averages adjacent frames. And I get a pretty nice picture. So it's some kind of an emanation from the display or the cable or something. I tested this from the other room with a bigger antenna, which is the 9-element Yagi that I use for my PMR activities, listening activities. And when we get the frequency right and the frame rate just right, we are indeed able to synchronize it. The image is slightly more noisy, but especially if we average some more, we can get a pretty nice picture. So this became my remote HDMI viewer. Now, as I said, the center frequency of the signal emanated by the HDMI display is integer multiple of the pixel clock. But HDMI should be digital. So why on earth would it be transmitting analog video? Well, it turns out that HDMI transmits color values as 10-bit code words, and each code word, this is my speculation, each code word produces a very specific amplitude in the emanation, and it's very predictable in the way that the 10-bit batch pattern stays the same from frame to frame. And because monitor video tends to be very static, it's very easy to average between frames or integrate. Now, it's not possible to get a perfect copy of the digital picture on the computer display this way. For one, the sampling rate of the radio is only 10 megasamples per second, which is not quite enough to get everything that's going on the display. It's not a raw signal we are hearing, it's rather just an artifact. And there appears to be an echo from all the sharp edges in the image, some kind of a wavy pattern. I'm not sure what it is, but I think it's some sort of a reverberation in the cable, maybe. Could be. And also there's no way to receive color information from the display. As far as I know, the color signal in HDMI is spatially separated in the cable. So there's no way of knowing which color channel emanated which part of the signal. It's just one big lump of amplitudes. This picture demonstrates some of the shortcomings of this eavesdropping method. On the top is a raw signal that I sent to display, and on the bottom is what I received on the radio. So here we can see that the sharp edges produce this kind of a weird wavy pattern. And we can also see the wavy pattern on the left, that's resulting from the horizontal synchronization signal, which is very strong. And this effect completely blurs most texts, for example. And we can also see that the grayscale, individual grayscale values map to very random amplitudes. So photos and video will look very distorted because there is no linear mapping from grayscale value to amplitude. And we also see that color is probably not possible because the red and blue gradients seem to produce a very similar kind of pattern. Here I try to average the echo effect from adjacent scan lines, actually all the scan lines in one image, and then use this signal as deconvolution kernel to remove the echo. But the results were not very good. It was very noisy. And also it was very expensive for the CPU. Now this effect is nothing new. Wim van Eck already in '85 wrote a paper about it. And that's why this kind of thing is often known as Van Eck freaking. He wrote about CRT displays especially, but in 2004, Markus Kuhn wrote about a similar attack against flat panel displays. And in his article, Kuhn suggests some mitigations. I think he mentioned LSB noise, or adding a sort of randomness to the least significant bit of the video so that it breaks the mapping of grayscale value to amplitude. And so it cannot be reconstructed at the radio receiver. Or you could also use smaller fonts so that it blurs them out more easily. And I'm not sure about this, but depending on how the signal is emanated, maybe some sort of insulation could work, or using shorter cables to minimize the antenna effect, but I'm not sure. I'm not sure how it's actually emanated from the display. This sort of thing is not a problem in HDMI 2 or DisplayPort protocols because those are either scrambled or encrypted, so there is no, so the pixels from frame to frame have no correlation. So how does it all relate to PAL video? Well, later, when all this was done, I wanted to record video from my NES console on the MacBook. But it turned out to be more difficult than I expected. I ordered like a cheap video capture device from eBay, but it took a long time to arrive, and then when it finally arrived, it turned out that the Mac software would only support NTSC. So the color, there's no color at all. And I tried filming the CRT display with the camera and even the flat panel display with the camera, but the results were not very good. So then I thought, I have this remote HDMI capture code. Could I use it to decode the video signal from the NES? Because the NES has a radio frequency output that the AirSpy R2 could well receive. It's at the 55 megahertz frequency. So for reference, here is a PAL signal. This is one scan line in an image. So we have a horizontal synchronization signal, just like in our HDMI capture. And then we have something called a color bursts and a high frequency video signal, which takes most of the scan line. A PAL video is normally interlaced, which means that not every scan line is sent in every frame. But luckily, I don't have to take this into account because the video from the NES is progressive scan. Color in PAL is a bit peculiar. It's encoded in a subcarrier, and there are some phase shifts from line to line and all that kind of stuff. But I was willing to try. And I was quite quickly able to adapt this HDMI code to play Super Mario using my MacBook as a display for the NES. And the delays are actually pretty short from the radio to the display, so that it's a bit cumbersome, but I can actually play it. But it's still in black and white, so we need to take a look at PAL color. Here we see the video carrier from the NES. It's an AM carrier, and it just fits in the 10 megahertz bandwidth of the AirSpy R2. Now the chroma signal, which is the color signal, is on a subcarrier at around 4.5 megahertz. But on the LSB side, you can see something nasty going on. It's the audio signal, which is very close to the video signal. That is an FM carrier right next to the video signal, but it has been aliased on top of the video signal because the filter is not sharp enough, and it's way too close and way too strong for the filters. So I was kind of worried that the chroma signal would be completely destroyed by this, and there is really no way to avoid this. So I had to use a notch filter, a very narrow notch filter, to filter out just that frequency. Now the audio is FM, so it's very difficult to completely remove it when there is modulation, but at least I could get the middle frequency out. Here's one of the first color decoding results. I simplified it quite a bit. For example, I didn't use a COM filter, which is sometimes recommended for the PAL chroma signal. I used a simple bandpass fur filter, which is pretty CPU intensive. And I also couldn't get the alternating phase right. So my solution after this image was to simply ignore the color information from every other line and just copy it over from the previous line. And actually it's pretty unnoticeable, especially in a moving image. In this image, there's still some bugs. For example, there's no green color at all, but this was only a minor bug in my code, and I was eventually able to get a nice color picture Here's just a comparison of the Tetris title screen before the notch filter and after the notch filter. So the notch filter is able to remove quite a lot of the noise, and also it improves the synchronization of the color carrier, I think. Yes, a short demo of the decoding the PAL code in NES Tetris. So it's running on a 2013 MacBook Pro in real time at 50 FPS. The resolution is 240p, which is the native resolution of the NES. Okay, now we can move on. Here's a schematic diagram of the receiver that I wrote. So on the left, it's the AirSpy inputs and the notch filter. It's the very first thing that happens even before the amplitude demodulation, which follows. And then we invert the result of the amplitude modulation from unity, because broadcast video signals are sort of inverse AM to save power on the transmitter. Then we just copy the whole signal directly on the grayscale channel without any sort of filtering. I think it's good enough. It generates some noise maybe, which could be filtered out, but this is just a performance thing. And we synchronize the scan lines to a 15 kilohertz clock. And then the center part is the color decoding. So we use simple bandpass FIR to get the chroma signal. And then we synchronize a 4 megahertz, 4.43 megahertz carrier to the chroma signal. And we do an arbitrary phase shift because I didn't get it right. I had to sort of estimate the number of degrees to rotate the chroma. So it's a bit like an old TV where you used to have the hue wheel that you could manually adjust. Some profiling. Here we see that most of the CPU cycles are used in the audio notch FIR. So that is quite expensive. I'm using, I think it's 1000 coefficient filter. So it might be a bit overkill. And another FIR filter in the chroma decoding circuit is responsible for 12% of the cycles. I'm using STL textures to draw the image, which is kind of efficient. Yeah, some performance considerations. The computer should be able to demodulate the image at 50 or 60 FPS. And there can be no missed samples, so it has to be kind of a real-time system. Because when you miss samples in the video signal and you don't know how many samples you missed, you lose synchronization and it looks very nasty in analog video. I exploited multi-threading pretty much. So all the pre-filtering is in its own thread, and the AM demodulation is in its own thread, and the UI is in one thread, and so on. And as I said, STL textures is what I use to draw the image. And I used Liquid DSP, the library for this. But I see no reason why this couldn't be implemented in other libraries like GNU Radio. something that I wish my program had. It should be even more efficient because my laptop is old and I want to do other things with it, and I don't want it to get very hot when it's running. I want to use a radio with a slightly wider bandwidth. Now I know that the AirSpy should be capable of doing wider bands, maybe with a custom firmware, but I haven't tried that. I could maybe try with the Hack RF or something like that, so that I could accommodate the audio carrier and maybe filter it out properly. I'd like to rewrite the color demodulation code so that it uses something more clever and maybe uses all the scan lines for the color. And I would like to have this code support interlaced video so that I could, for example, watch VHS tapes. So thank you. I hope you enjoyed and found this interesting.
Hi, I'm Derek, one of the GNU Radio Conference organizers, and I want to give a quick update about the chat situation. One of the fun things about Matrix is that as an open source tool and with a really good relationship with our hosting providers, we get kind of some inside information. Right now, there's one thread that's CPU bound that's slowing down all of the chat. And sorry, have the YouTube channel open. And so right now, the chat backlog is kind of extending indefinitely. They're going to take the chat down for 5 minutes and move us on to a higher performance cluster that should be stable for us for the rest of the conference. So thanks for your patience. This won't interrupt the live streaming of the videos, thankfully. And also, if you have a workshop, that also runs on an entirely separate platform. So that also won't be affected by these performance issues. We hope that the chat will be back up and usable in the next couple of minutes. Please do just kind of keep trying it every few minutes, not constantly refreshing, and hopefully we'll be back up and running by the time the next talk starts, which is in 15 minutes. The Q&A for Oona's talk, unfortunately, is going to be a little bit difficult, but hopefully she'll be around later to answer some questions, and we'll do the best we can. Thanks very much for your understanding and patience, and we will give you an update just as soon as we can. Thanks. Hi, quick update. The chat server has now been turned up to an 11 on the CPU side, and we're seeing things running much more smoothly. So if you took a break from the chat, please do try returning, and we think it'll be more successful now. The next talk up is one of our lightning talks. This is I hope, looking at the schedule, this is one of our perennial events, and of course I've done this again. Lightning talks are one of our perennial events where we have members of the community and other short 5-minute talks come on board. So I'll return you to the stream. Hope to see you in chat. Thanks very much.
Hello, I'm Richard Stanley, and I wanted to share a project that I've been working on around how to see transmitters that are really, really nearby, like in my dining room nearby, and how to kind of visualize those in a heat map to show angle of arrival and to show magnitude. So there's so many things on YouTube that are awesome that get into radio stuff, and this is one that I found pretty inspiring, which is a presentation by Natasha Hurley-Walker, who's a radio astronomer in Western Australia. And the folks there have an enormous array of dipoles in the desert. And they're able to create these kind of, post-processing, of course, but they're able to create these kind of amazing radio views of the Milky Way. And so just to kind of learn the basics and reinvent the wheel in order to learn, I wanted to build something that could detect very simple things in a very confined environment. And so I wanted to use GNU Radio and to use some SDRs. And again, this is a work in progress, so there'll be issues that we'll discuss. First thing I'd like to show you is a simulation. This is a 2D simulation. All the simulations and everything are available in my GitHub. And the hardware tests as well. So in this simulation, what's happening is that I'm moving around a transmitter, kind of a pseudo transmitter, simulated transmitter, with regard to its phase, in both azimuth and elevation. And the top thing is elevation, next is azimuth in these Qt GUI time raster sinks. And on the left is a video SDL sync, which combines those. So what this shows is that as you move the transmitter around, you should be able to visualize that in the time raster sinks, but also together in the video SDL sync. And this is the goal, right? So this is how I kind of tried to figure out the math and how to do it in GNU Radio. Okay, so how this is working under the hood is that let's say a radio signal hits one antenna before it hits another. Those are separate radios, and therefore, if you lag a signal with regard to the other, you should be able to see the energy in that direction, right? And same as the other way. So you lag one signal with regard to another, you should be able to see the energy. So you lag, and then you combine those signals, and then you can create an array of pixels in which the brightness or the darkness represents energy, and you have it for each of those kind of steering vectors or weight vectors. GNU Radio looks like this. You take signals from and this is a one-dimension example, right? So it's just 2 radios. So you take signals from the left RX and the right, left and right, so like an azimuth, and then you lag their phase, and then add them together and take the magnitude. Okay, excuse me. Only the best. So Legos for holding the antennas, eBay log periodic dipoles, and actually great radios. So these are Ettus user B210s, and these are phase coherent within themselves, right? So there's two receive, 2 transmit on these. I'm not using the transmit, but so there's 2 receive. So in one B210, they're phase coherent, which means you can resolve the differences at a pretty small, number of radians or degrees between signals. And there's one for each dimension. And then there's a ham HT used for the transmitter. There's a couple of mini circuits attenuators on there. I already blew up one daughter board accidentally in doing this, so pay attention to link budgets. All right, so I'll do a demo. This is a one-dimensional demo. So this is just 1 B210 and 2 antennas. All right, so as I move the radio around, you should see that there is some tracking of it in terms of direction of arrival as well as magnitude. So the brightness or color, it depends on which view you're looking at, represents the magnitude, and then angle of arrivals being represented by the by where that's moving. So that's one dimension. That's pretty straightforward, and a lot of fun, actually. All right, so now I'll get into the work in progress. This is the 2-dimension example. This is a little more complex, and I'll explain why. Mostly not because of the math as much as my limitations of my antennas. So as you kind of move the transmitter around an axis in which the polarization is lined up between the receiver and the transmitter, no problem. So if you're like this with elevation, like this, with azimuth, no problem. But when you get in the corners in these quadrants, like it breaks down. So it sort of works, but I think this requires some new antenna. So if anyone knows how to get circularly polarized 70-centimeter antennas that'll fit in my dining room, that would be great. And I think that will kind of solve that issue. Okay, so that's about it. Thank you for attending. And if you want more about, listen to a real expert about phase arrays and beamforming, John Kraft, the Analog Devices, is running a workshop on Thursday. Look forward to that. That's going to be great. And also, there's some fun stuff in GNU Radio 3.9, which is coming out in coming months, and that has a lot of fun stuff. Thanks to Mike Piscopo. And if like me, you're having fun with this and you want to enjoy some YouTube videos, GRCon 2017 is just so amazing for this. They're fantastic presentations by Travis Collins and Sam Whiting and Ben McCall and Will Myrick. So please check those out. Those are just great fun for DOA and beamforming stuff. Again, I'm going to put all the flow graphs and demo stuff and all that kind of stuff in the GitHub repo, citizenrich/seeing signals. Thank you, and have a great conference, and be safe.
James Kulp has more than 30 years of experience in the real-time computing industry. Currently, he is a consulting software architect involved with several DoD-related embedded architecture efforts. He previously was the architect for scalable heterogeneous multi-computer operating systems at Mercury Computer Systems. Before joining Mercury, Mr. Kulp served as a product architecture consultant and board member of Surety Technologies. He was a systems software consultant for operating systems analysis and remote management at Digital Equipment Corporation, founder and vice president of Superscript, which made tablet-based systems, vice president of Intelligent Data Acquisition Subsystems Technology for Event Technologies, and founder and program manager at Symbolics. Mr. Kulp has also served as the Computer Services Department head at the International Institute of Applied Systems Analysis, and was founder and vice president of technology for Graphic Management Systems. Mr. Kulp attended the Massachusetts Institute of Technology, where he studied computer science, management, and architecture.
Good morning. At least in the time zone chosen for the conference schedule, it's morning. I'm Jim Kulp, architect of OpenCPI, and I'm going to be talking about OpenCPI and how it can serve as an infrastructure for GNU Radio and GNU Radio Companion. Today, we'll talk about how OpenCPI can address the diversity of hardware and firmware in SDRs and how that can help with GNU Radio. First, we'll talk about hardware diversity in SDRs, and then how OpenCPI works with GNU Radio and GNU Radio Companion on diverse radios. Next, we will describe the kinds of development processes that are supported in OpenCPI. This includes how it supports developing components in this environment, how you develop support for new hardware, and of course, using GNU Radio Companion, how you construct applications. Finally, we'll wrap up with why and when we think OpenCPI should be used and a roadmap for where things are going next. This is the overall picture of how things fit together, and we will go into more detail shortly. Under GNU Radio Companion, we add OpenCPI blocks for CPUs and FPGAs to the existing GNU Radio blocks and run them all together on a combined runtime environment that includes hardware drivers on both CPUs and FPGAs. Let's start with the basic idea that SDRs can be built in many different ways with different parts, chips, processors, but they all have a common structure, which is that there is some configurable hardware near the antenna. There's some programmable processing resources that do the SDR processing, sometimes called modem processing or waveform processing or just signal processing. And then finally, there is a user interface to what this radio is doing, or some services software that is making the radio a service integrated into some larger environment. So we have the interface between the hardware and the SDR processing, and the interface between the SDR processing and the user interface or services integration software. Nearly all SDRs fit this model, even when the SDR is in fact a laptop PC with a USB dongle plugged into it. So let's investigate this idea that SDRs are built in many different ways with diversity of design across vendors and within vendor product lines. Our first example is what is perhaps the smallest and cheapest SDR, the RTL SDR USB dongle radio, which consists of some configurable tuner receiver hardware that plugs into a PC. It has no FPGAs, and all the SDR processing as well as user interface software runs on the PC. Our next example is one of the many radios available from Epic Solutions. And in this case, it uses the popular ADI transceiver front-end circuit. It has a small FPGA, and it has a USB or PCI Express connection to a host PC. So in this case, the front end is more powerful and configurable than the previous one. Some time-sensitive processing can happen in the small FPGA, and the rest of the processing has to happen in the PC that it is plugged into. Our next example is the small Pluto radio from ADI, called their Advanced Learning Module, and it has the same front end as the previous radio. It uses a Xilinx Zinc chip, which has both an FPGA section and an ARM Core CPU section, connected on chip using an AXI interface, and it also has a USB or Ethernet connection to a host PC. The FPGA is quite small, the smallest of that product line, but it can do significant processing. The ARM CPU in the same chip is available to assist in processing in close proximity to and thus reduced latency with the FPGA processing. and higher level processing can, as usual, be offloaded to the attached host PC. Our final example is the Ettus X310 radio, which is a powerful member of their broad product line of radios. The front end is not just a chip, but a powerful combination of RF transceivers and higher speed ADCs and DACs for higher speed sampling. There's a large FPGA, and this radio is attached to the host PC via PCI Express or 10 gigabit Ethernet. In this case, there is a lot of capacity for processing in the large FPGA, and there is a high performance, high bandwidth connection to the host PC or whatever processor it is connected to. And so a lot of processing can happen in the FPGA and perhaps less being required in the host PC. As you can see, there are many different ways radios are built with different types of processing happening in different places. The challenge is how and where do I put my SDR processing, or in GNU Radio terms, the blocks in my flow graph. There are many ways it can happen on different processors of different types with different interfaces for the data flowing between blocks on different types of processors. This is hardware diversity in SDRs. We just looked at hardware diversity in SDRs and how they're put together and how different they can be. And now we'll look at the other side of it, which is how they are programmed. Happily, GNU Radio and its runtime and the GNU Radio companion solves this problem for what runs on the primary CPU. You have one way of writing blocks, a common runtime, a common user interface, regardless of how the radios are designed, which is a great thing. So for our first radio, GNU Radio needs to have source blocks that talk to the vendor's API, and thus the vendor's library, which of course knows how to talk to the hardware in the radio. That's a pretty simple situation because there is just software and just software on the PC, but it is a vendor API talking to vendor hardware that is mostly two easily available chips, one of which has a normal datasheet and the other one has a reverse engineered feature set. Our second radio from Epic is programmed with their API and their library, and since they have an FPGA in this radio, they also have a reference design for the FPGA and have what's called a platform development kit to enable customers to customize the processing on the FPGA. They also have some hardware access capability, some from the FPGA and some from the processor. If it isn't obvious so far, the cross-hatched blue and green boxes in the diagrams are a mix of or choice of FPGA and CPU processing. Our third example radio, the ADI Pluto, also has an API called libIO, and ADI includes Linux, DMA, and device drivers. And on the FPGA that's in the Pluto, there are reference projects and a library of IP blocks. And the hardware access in that radio is nearly all from the FPGA, so the FPGA talks to the devices, and the host CPU talks to the embedded ARM CPU, which talks to the FPGA. Our final example radio is again the Ettus X310 with the big FPGA, and Ettus has their API called UHD, which provides source and sync blocks for GNU Radio using that UHD API. Ettus also provides a serious FPGA toolkit called RFNOC, which constructs processing configurations for the FPGA. The radio front-end hardware is accessed entirely from the FPGA in this radio. So the summary here really is that we have 4 vendors, 4 APIs, and 3 FPGA toolkits. So our conclusion is that there is a lot of diversity in SDRs, different types of processing, different mixes of processing, different ways of connecting processors, different hardware vendors with different APIs, SDKs, and toolkits. I didn't mention it before, but the FPGA chip vendors themselves have toolkits that are very different, and even the various FPGA simulation tools are different. So OpenCPI brings consistency and commonality to the parts of SDRs that GNU Radio has not focused on, where SDR processing is mixed between processors of different types, and the programming models and tools have been vendor specific. Much like Linux provides a common environment for most embedded processing with device drivers for different hardware elements, OpenCPI provides an analogous model for the FPGA environment, also with the equivalent of device drivers. While there are only tens of developers expanding and evolving OpenCPI, Linux has thousands, but we believe we are achieving a similar objective of a common model for all of SDR processing. So I'd like to summarize here what OpenCPI is and describe some of its important attributes. It is open source. It is a component-based environment like GNU Radio. It is a development and runtime framework. There are tools for the development process as well as runtime libraries and drivers to deploy and run applications. OpenCPI is designed for embedded systems on diverse hardware. That was its first and primary purpose when it was designed, and that remains the priority during its evolution. When we say diverse hardware, we're talking about different types of processors, including FPGAs, with components executing across all the processors and types in the system. This requires device driver models where sometimes device code is written directly to hardware, but sometimes it is simply using existing open vendor-supplied code for their hardware, which is then integrated and wrapped into OpenCPI. SDRs, usually with GNU Radio, are really the most important class of embedded systems for OpenCPI. So the primary purpose here is to enable applications to target diverse hardware, and that diversity can be upfront, meaning I know the 5 systems I want my application to use in different situations, or I want to know that my application will be easily moved to new hardware platforms in the future if I use this framework, even for platforms I am not aware of yet. How exactly does OpenCPI relate to GNU Radio and the GNU Radio Companion? First of all, they are both component-based environments, and so the concept of a GNU Radio block is similar to the concept of an OpenCPI component. We'll get into more detail on that in a minute. A GNU Radio flow graph, which is an assembly of blocks that will together perform some function, is the same concept as an OpenCPI application. OpenCPI uses the GNU Radio Companion as an application builder so that it is the same user interface used by GNU Radio users to build applications and flow graphs. We have modified the GNU Radio Companion so that it can build and run OpenCPI applications across CPUs and FPGAs, in addition to its current function, which is building and running GNU Radio flow graphs. OpenCPI is currently being modified to execute most GNU Radio blocks as part of the overall heterogeneous application. In other words, the runtimes are being connected. Since OpenCPI is an infrastructure, it can thus act as a vendor-independent heterogeneous infrastructure for GNU Radio applications and enable them to more easily migrate to diverse hardware. Now we'll describe OpenCPI in more detail by describing the 3 distinct development processes it supports. The first one, component development, is what creates the libraries of components for applications to use. The second, platform development, creates the support packages for new hardware. And the third, application development, uses the results of the first 2 to create and deploy SDR applications. So now we'll discuss component development in more detail. Component development in OpenCPI creates the building blocks for applications. Just like in GNU Radio, you create blocks, at least in part, using the GRmod tool, etc. But in OpenCPI, there is a clear separation between the component specification, meaning the contract or the functional definition, and the implementation of that component. The component has an XML-based specification, a unit test suite, and a data sheet describing what that component does. And then we have, separate from the component spec, implementations, which are source codes that implement that specification. We call these workers. So a component is really a collection of these source codes and a common spec that they all implement, including a common unit test, so that when we test them, we know they all implement the same functions. It is common to have workers written in different languages for different processor types, such as C++ and VHDL. The deliverable from the component development process is a library of related components, each of which has specs, unit tests, documentation, and some workers. This creates a deliverable that is ready for application development on diverse hardware, since the components have different workers that can run on diverse hardware. This all means that the application development process can experiment using different workers on different processors simply by directing the execution of the component to be on a different processor, which will automatically use the appropriate worker. Note that in the example component A in the diagram below, we have a C++ worker, a VHDL worker, and a third worker that is also VHDL, but optimized for Xilinx FPGAs. To elaborate a little more on the concept of components and workers, this diagram shows a component, encrypt, and there are two APIs or authoring models or ways to write workers represented by the HDL and the RCC. Each of those authoring models supports one or more languages to write the worker for that API or authoring model. And we have examples of VHDL, C, and C++. The VHDL language might result in two different source codes, one that was big and fast and used a lot of resources but ran fast, and the other one was very skimpy on resources but was slower. And we might have a C version that is designed for small processors that might not even have a good C++ compiler, and then a normal C++ worker. Each of those could be compiled for appropriate targets, and thus delivering a library could deliver all the workers and all of their compiled results for a wide variety of targets. So next, we'll move on to the second development process in OpenCPI, platform development. Platform development is the process for creating a deliverable that enables OpenCPI on new hardware. And usually it is a package that contains whatever is necessary to support all the new hardware on a given system. For embedded processors running software, the package might contain or refer to cross tools, kernel headers, boot files for what we call the software platform in the system. For FPGAs, the package might contain or refer to tools, drivers, loading mechanisms, including descriptions of slots for daughter cards. The structured deliverable is what we call an OSP, an OpenCPI System Support Project, which is analogous to the less well-defined idea of a BSP or board support package. Since the support for embedded processors, embedded FPGAs, and devices in a system are all modular, that means an OSP might not contain some of them if they are already existent elsewhere. In the example deliverable here, there is a device driver for an ADC, analog to digital converter, which means that driver was not already supported in OpenCPI for a previous system. The FPGA in this case is the FPGA part of the Zinc UltraScale system on chip from Xilinx. And the software platform is based on the Xilinx cross tools and kernel from their 2019.2 release for 64-bit ARM processors. This software platform would be the same as for any other Xilinx-based 64-bit ARM CPU. So even that support might not need to be in this OSP. This table presents supported devices and platforms. The first row is what is supported in 2.0. The second is what is under development either by the OpenCPI team or known to be under development by third parties. And the third one is where we know there's intention to do these and to work on them, but they're not under development yet. Important point here is that platforms or a system or an OSP consists of all the supported pieces. And so frequently an OSP will have pieces that are already supported for other systems. And that's why we have columns like transceivers and interfaces and FPGAs and tools, because a typical OSP picks from the existing supported elements and then just fills in the gaps. So finally, we'll discuss application development, which is the third development process in OpenCPI. Application development is, of course, built on the results from the previous two development processes. It assembles components into applications using the GNU Radio Companion to assemble blocks into those applications, just like it does for GNU Radio blocks into flow graphs. And given the available component libraries, applications are ready to run on diverse hardware because those libraries contain diverse implementations of components. An application is represented by an XML file, or in some cases, a custom C++ main program, which uses what we call the application control interface to launch, configure, and control the XML application. There's also a prototype of the application control interface in Python. The deliverable for the application is the XML specification, or in some cases, the executable using the ACI, and then packaged with that would be the workers that have been built for the desired targeted software platforms, as well as the FPGA configurations for the potential targeted FPGA platforms. Component libraries used by application developers can come from a number of different places. The first being the built-in projects in the OpenCPI repository, which contain a basic set of components. And then there are other OpenCPI projects that are in other repositories in the OpenCPI GitLab site, usually contributed by various third parties. And of course, component libraries can exist in other places that are internet accessible, or even privately inside other organizations, hopefully temporarily before being contributed back. Component libraries frequently use available source codes from existing libraries when they are available as open source with acceptable licenses. The table below is just a categorized set of possible components, some of which are available now, some are under development and about to be contributed, and others are awaiting development or contribution. So we'll wrap up by discussing why and when OpenCPI should be used, and then a short roadmap of what's coming next. For application developers, what's interesting about OpenCPI is that it is designed and built to be ready for diverse hardware. Diversity of hardware structures, hardware processors, and vendors. So if you need to deploy on diverse hardware now, that's good, and you know the hardware you are deploying on. If you want to be ready for the hardware you don't know about, or you want to easily reconfigure your applications to move processing from one type of processor to another, depending on which has the heavy load or whether you have latency problems, then OpenCPI can be a valuable alternative for application development. Also, from a team and developer point of view, you have a common workflow as you develop component libraries and applications. So you are not switching tools and requiring new training, and thus have easier movement of people between applications, projects, and systems. OpenCPI achieves this since it has the commonality of the workflows and methods and terminology and concepts for component and application developers targeting diverse hardware. For hardware owners and developers, there is a different set of benefits from OpenCPI. Device-level drivers are widely applicable across platforms because the same chips are used in different systems from different vendors. And it is common for a new system to be enabled using drivers that already exist, which is the same model as embedded Linux, where the developer of a new system using embedded Linux would use existing drivers. Also, there is a structured process for delivering hardware support. Because it is key to OpenCPI, a lot of effort in the tools and documentation and packaging makes this process well defined. There is a workshop later this week that will elaborate on that process. Also, because the available component libraries are already heterogeneous, the new hardware platform usually has component libraries ready to be used and tested. Finally, for small and new hardware vendors, you can avoid the time and expense of creating an SDK that is targeted for your own product line and instead simply use OpenCPI. This is the short-term roadmap for OpenCPI for the rest of this year and next year. OpenCPI 2.0 was recently released, and going forward, there are multiple teams with multiple organizations that are improving and evolving OpenCPI with the following major priorities. First, further GNU Radio and GNU Radio Companion integration with OpenCPI. What this means is building on the current dual mode GNU Radio Companion, which already allows building and running GNU Radio flow graphs and OpenCPI applications, but they don't really mix together. So the next major effort is a runtime integration where applications can combine components and blocks from both frameworks. On the hardware side, there are efforts to support more of the product line from Ettus, more of the ADI development and system on module products, more of the EPIC SDRs. Support for the RF SOC technology from Xilinx is under development, and the Cyclone 5 and Stratix 10 based systems that are based on the Intel FPGAs are also under development. We are always looking for ways to make applications ever more portable across diverse hardware, and there are a few improvements we will make in this area as well. And finally, we are going to refresh the OpenCL support for graphics processors, which was previously done in OpenCL 1.2, and we want to update and refresh that for OpenCL 3.0. Here are some useful internet addresses for getting more information about OpenCPI. And there are two workshops later this week at this conference. One is more of an introduction to using OpenCPI with GNU Radio Companion. The other is an introduction to developing new hardware support for OpenCPI. Due to demand, each workshop will be given 3 times. And hopefully, we now have some time for questions using the messaging set up by the conference. Thank you.
The title of this talk is Community Continuous Integration for GNU Radio and OpenCPI. Hi, I'm Arlen Poole. This talk builds on the previous talk, OpenCPI is an infrastructure for GNU Radio. OpenCPI brings the capability for GNU Radio applications to exploit the hardware of embedded heterogeneous processing systems and be deployed on diverse hardware. In the first part of this talk, I'm going to present how do you assess whether your GR OpenCPI application is ready for diverse hardware. In the second part of this talk, Willie Thompson of Centauri will present a case study of enabling a GNU Radio application to exploit OpenCPI. For this case study, he's going to use the GNU Radio ADS-B receiver application. When is a GR application ready to deploy on diverse hardware? That determination requires that the developer have access to a diverse set of development and testing hardware assets. In most nearly all cases, the developer will not have direct access to a variety of different hardware configurations. In seeking to address this issue of developer access to a set of diverse hardware assets, the OpenCPI team has a roadmap with 2 CI facilities. The first is a dedicated CI hardware test center for continuous testing, and that's separate from the dedicated development lab to support OpenCPI and software and support platform development. The focus of this talk will be on the Community CI Test Training Lab. As I mentioned on the last slide, we have a dedicated CI hardware test center for OpenCPI continuous testing. Continuous testing for both OpenCPI and supported hardware platforms. This is a dedicated CI hardware test center that exists today. It's a stable, lights-out resource with configuration control. Hardware-in-the-loop testing is being added for additional supported platforms, and testing scalability is provided using AWS. Assets include supported hardware devices and platforms, the required versions of software tool chains and simulators, and supported versions of operating systems and system software. OpenCPI's CI testing strategy exploits OpenCPI's heterogeneous unit test system, uses GitLab's CI tools, and baseline testing is kicked off by commits and merge requests. Full build and tests are performed on weekends, and this delivers a continuous test coverage for OpenCPI's software and gateware on all supported hardware. As I mentioned a bit earlier, the OpenCPI roadmap includes a community CI test and training lab. The first instance of this community resource is the GRCon 20 OpenCPI workshops. We're standing up this workshop lab as an initial dry run to the community, and the workshop lab is populated with 20 plus of the analog devices, Plutos, an Ettus E310, and Linux servers. There's remote access is controlled through a VPN. This is really a prototype for our community resource. We're gaining experience with both requirements and implementation. After GRCon 20, we will transition to a more complete capability and have policies for access control and scheduling and populate it with additional hardware. The ultimate objective is for assets to include all supported hardware plus third-party provided hardware that's either co-located or remote. This provides community-controlled access to third-party provided hardware. This community CI test training lab will provide different benefits to different stakeholders in the GR OpenCPI community. The stakeholders who will benefit include GR block and OpenCPI component developers, application developers, prospective users and projects, and also hardware vendors and integrators. Now I'm going to address how each of these parties will potentially benefit from access to a community resource. The benefits for GR block and OpenCPI component developers' access to a community CI test training lab is that it allows the testing of blocks and components on a diverse set of hardware that they may not otherwise have access to. This helps ensure overall portability, and developers can perform both unit testing and development and testing of example applications. It also allows testing across multiple processor architectures and configurations to characterize both performance and resource usage. The benefits for application developers of a community CI test training lab is that it allows them to test applications on a variety of hardware configurations. It allows experiments to be performed with different hardware configurations, such as a general purpose processor and FPGA implementations, to assess performance and resource usage. This improves the readiness to support future hardware configurations, as these experiments have provided additional insight into both performance and portability. The benefits for prospective users and projects of a community resource is it allows the prospective users to gain clarity into the supported hardware configurations and their stability, sort of a kick the tires. It also allows them to test available components on candidate hardware and do some experimentation with different hardware and hardware configurations to understand what may be most suitable for their application requirements. Also gives them an insight into performance and resource usages. The benefits of community resource for hardware vendors and integrators is that by providing access to their platforms, hardware vendors can ensure that their platforms get tested and characterized as both GR and OpenCPI evolve and as their hardware evolves. Prospective users then can assess the vendor-provided hardware, and applications can be characterized on custom configurations and platforms created by system integrators. In summary, the Community CI Test and Training Lab is going to provide benefits to the overall GR OpenCPI community. The use of the Community CI Test Training Lab enhances the readiness of GR OpenCPI applications to support diverse hardware. Now I'm going to turn it over for part 2 of the talk for an OpenCPI case study, which will be presented by Willie Thompson of Centauri Corporation. He's going to talk about enabling the GR ADS-B receiver application to exploit OpenCPI.
Hi, my name is Willie Thompson. I'm a senior cybersecurity engineer from Centauri. I will be presenting our OpenCPI case study for the ADS-B receiver. This briefing serves as a primer for a detailed discussion, a part of the OpenCPI workshop. Over the last several years, ADS-B has been used as a good reference design to demonstrate different GNU Radio applications. The key aspect for the receiver is being able to detect the preamble and then demodulate the post position modulation. For our design, we'll be concentrating on the 180-bit mode S message. The fundamental question for this community is why OpenCPI? OpenCPI provides a flexible framework for component-based design using multi-layer specification for components and workers and interface specification for custom protocol design. In addition, it supports heterogeneous operation. You can design for GPP, FPGA, or GPU. And lastly, OpenCPI supports deployment across new platform types. This allows for the optimization of algorithms for increased performance. The primary goal for this case study was to translate a GNU Radio implementation of the ADS-B waveform to a OpenCPI embedded device. During this process, we was able to develop RCC and HDL component libraries to support heterogeneous operation of the waveform. In addition, we leveraged the OpenCPI system support projects that support several platforms, including the E310 and the Pluto SDR. The hardware demonstration will be a main focus in the OpenCPI workshop that will be given later on in the week. The first step is the OpenCPI component definition. For our use case, we actually concentrated on a one-to-one relationship between the RCC and HDL worker implementation to support heterogeneous operation. But this is not always the case. It really depends on what type of deployment strategy you will have on the embedded system to dictate what type of workers you require for the different components of your waveform. During the OpenCPI component definition, there's two levels that you have to define. The first level is the OpenCPI component specification. At this level, you focus on the port definitions. In particular, you implement a OpenCPI protocol specification. This specification defines the opcode, format, structure, data bus of that interface. Each interface can have the same protocol specification, or can have a different protocol specification. In addition, you actually define your component level properties. These properties are properties that are associated with both type of workers, RCC and HDL. The different worker types can have additional properties and parameters defined. And that definition specification is called the OpenCPI worker description. The worker description for the HDL is very important. In particular, for the HDL workers, you have to define your port width, which is not the case for RCC workers. So you definitely will have to define your worker description interface attributes for each port width, bus width that you use for your input or output, or any interface that you have with your HDL worker. Lastly, we actually did a data rate analysis doing this component definition, because we were really interested in heterogeneous operation, and based on the different worker types, you may have bottlenecks that you have to take in consideration when going from a RCC worker to a HDL worker. So we strongly encourage you to do some initial data rate analysis doing the component definition. As you can see with the diagram above, we actually highlighted the samples per symbol throughout our algorithm. We actually defined the component level specification. Each of these may have additional worker description definition associated with them. In addition, we are looking at Q15 data notation throughout our algorithm for the ADS-B. Next, I will highlight the RCC development for our case study. Here is the basic anatomy of an RCC worker, which consists of three main elements: buffer management, the work implementation, which is the run method of the RCC worker, and then finally the work return value, which is a RCC result data type. For buffer management, we initialize pointer to the buffer object associated with each interface. Each buffer object has several methods associated with it. In this case, we're using the size method to attain the buffer size of the input buffer to be used during the work implementation. For the work implementation, we need to process several opcodes associated with the protocol specification. The main opcode for this worker is the sample operation, as shown within the case statement code. For the sample operation, we simply multiply the input buffer values by a constant. This constant is a property of this worker, and we obtain the value of that constant through the properties method of the worker. For the other opcodes, we do nothing. We simply pass the input buffer to the output buffer for further processing down the line. Lastly, we must return a value for this worker. The RCC result data type has several values. The three we highlighting here is the RCC advance, which advanced the buffer to be used again. So the output buffer is processed out of the worker to be used downstream, and we obtain new data within the input buffer. The RCC done actually enters the worker into the finished state. Lastly, RCC advanced done actually advanced the buffer and enter the worker into the finished state. For our case study, we actually leverage all the work implementation of the GNU Radio library. Next, I will highlight some key aspects of our HDL development. Our HDL worker design methodology is based on a OpenCPI wrapper scheme. This wrapper scheme allows us to use standard VHDL development flow for the work implementation. Once the work implementation has been verified, that code can be wrapped into a top-level design. The top-level design focuses on the OpenCPI integration, which is primarily worker operation control. OpenCPI operation control is based on several metadata signal. For this design, we have a do work signal that is conditioned by data validity and work availability. In particular, we are using the valid signal associated with the input interface to indicate that the data is valid for operation. And we're using the ready signal associated with the output interface to indicate that the data can be accepted by a downstream worker before we actually do work. In addition, we are implementing a data plane scheme, which is new for OpenCPI 2.0. In this scheme, you can associate a clock with an interface. As a result, we can use that clock to actually run our worker. To enable this functionality within the framework, you have to use the worker description attribute clock direction. More detail can be attained within the user guide. One additional concept that we want to highlight for the HDL development is the concept of assembly and containers. Assembly containers are needed to create a bit file. The assembly is actually all the HDL workers associated with an application. So when you have an OpenCPI application, there should be a one-to-one relationship between the application that use HDL workers in the assembly. In addition to the assembly, based on how you want to deploy the actual application, there's a container. That container allows have additional device workers that are used to actually execute that application on that platform. The containers are associated with the board support packages of the different platforms. And for simulation, the XM is considered a container that simply execute the code. Here's a depiction of our OpenCPI application for the ADS-B receiver. You can see that have all the elements associated with the waveform. This is a hybrid design where we have HDL workers, which is a part of our assembly, and then we have two RCC workers to source and sync the data for this application. Lastly, we will talk about some OpenCPI component libraries that have been generated by this case study. In support of growing the community around OpenCPI, we have created several libraries that is open to the community. The first one is a general SDR component library, which you can see is divided into several different types. It's really, the RCC workers are really closely aligned with GNU Radio. In addition, we are actively developing HDL worker for these elements to support heterogeneous operations. In addition, we have two application-specific libraries associated with this work. That's the ADS-B, and also we have created a ZigBee library. All of these libraries will be pushed out to the community at sometime soon. As the third-party evaluator, we were asked to give our final thoughts on OpenCPI based on our case study. OpenCPI is a unified framework for open source heterogeneous design and deployment. It provides a flexible XML framework that describes all aspects for component, application, and platform. Throughout this presentation, we highlighted several of these specifications. It is our opinion that they are easy to understand and to implement. RCC development and operation is GNU Radio Lite. OpenCPI supports external libraries for rapid development. In particular, for this case study, we leverage the GNU Radio code base. Opcodes are similar to GNU Radio stream types. And finally, OpenCPI implement buffer-based operations for RCC workers. Next, OpenCPI fully integrate HDL tools for development and simulation. For our case study, we leveraged standard VHDL development flow for worker verification. OpenCPI integration focused on worker operation data flow via OpenCPI metadata signal. Third-party HDL primitive and IP cores are supported. Finally, OpenCPI allows for the deployment of application across multiple embedded platforms. For the ADS-B application, we are looking at the Pluto SDR and the E310. In addition, we are developing an OSP for the N310. For further detailed discussion about this case study, please join us at the OpenCPI workshop.
Thank you, Willie, for that presentation. As you can see, OpenCPI as an infrastructure for GNU Radio brings a lot of new capabilities that we believe are interesting and exciting for the GNU Radio community. For additional information on OpenCPI, please see the list on the screen. I'd like to take this time to thank the GRCon organizers and thank you for listening to my presentation.
Matt Knight is a software engineer and security researcher who thrives on solving meaningful problems. Please welcome Matt Knight.
Hi, GNU Radio Conference. Thanks for tuning into our talk on the Radio Resilience competition. Let's get things started with some quick introductions.
Hi, I'm Sid. I'm the founder of Radio Resilience, LLC.
Hi, I'm Mark from Agitator LLC. I am a wireless security researcher, and I really enjoy using software-defined radio to break proprietary protocols. I'm an alumnus of the Bastille Wireless Security Research Team. I'm also an alumnus of both of the DARPA software-defined radio competitions, the Spectrum Challenge and the Spectrum Collaboration Challenge.
My name is Matt Knight, and like Mark, I'm co-founder of Agitator LLC and alumnus of DARPA's Spectrum Collaboration Challenge. My interest in wireless communication technologies and signal processing tools like GNU Radio led me to the information security domain, which is where I apply most of my attention these days. We're speaking with you today to tell you about an exciting event we're hosting called the Radio Resilience Competition, and to encourage you to compete in it. We'll kick things off by providing some background about the competition, how we became inspired to host it, and the problems we hope to solve in doing so. The Radio Resilience Competition is in part inspired by DARPA's prior software-defined radio grand challenges, so we'll share how our experiences from competing in those are shaping the design of the Radio Resilience Competition. We will then transition into talking about the design of the competition, including its objectives, rules, and a walkthrough of the channel simulation infrastructure we have built for the event. Lastly, we will conclude with a demo showcasing how easy it is to get started. And now to tell you more about the inspiration behind the Radio Resilience Competition, I'll hand it over to Sid. Take it away, Sid.
Thank you for that, Matt. I've been running a software business for the last couple of years, but I also studied applied physics. And I had to go back in my 5th year of studying and go back and do one course that was left of my first year. It was electricity and magnetism. It was the hardest thing to do. And I never imagined myself going back to that. But when I found software-defined radio, I was hooked. It was super interesting and it's super approachable. So as I started getting into it, I found GNU Radio, which was awesome. And but I also discovered the DARPA SDR competitions, the Spectrum Challenge and the Spectrum Collaboration Challenge. And that got me thinking. And got me thinking about the progress in radio. Because I think one of the biggest benefits have been unlicensed spectrum. Now that we have unlicensed spectrum, where you don't need permission to broadcast, there's been so much innovation. I cannot live without Wi-Fi. And it's working because devices are well behaved. But I think we should put the bar higher. On the internet, we don't assume that everyone is well behaved. And I think that as things get bigger and there's more users and more devices, that will be the case for the radio spectrum as well. So we got to make sure that radio works, even if people are intentionally trying to interfere. And when we have protocols that can deal with that, I think it will make radio work better also when there's no interference, because it will just be more reliable, period. And to get there, I think a competition is a great way. A big inspiration is the ImageNet competition. It advanced the state of machine learning and artificial intelligence enormously in a couple of years. Because if you organize a formal competition, the participants can measure how they're doing. They can show that they've really improved the state of art. And that's what we want to do for radio as well. So I'll now hand it off to Mark, who will talk about how we designed the Radio Resilience competition.
Thanks, Sid. The design of the Radio Resilience competition was largely influenced by our experiences competing in the 2 DARPA software-defined radio challenges. I had competed solo in the first Spectrum Challenge as Team Wasabi, and then Matt and I joined forces as Team How Make Radio in Spectrum Collaboration Challenge. So conceptually, the first Spectrum Challenge was actually pretty simple. Each team was responsible for controlling 2 USRP and 2 TENs and transmitting packets over the air between them. The competition itself was carried out at the Orbit test bed at Rutgers, and in order to facilitate offline development, DARPA gave each of the finalist teams a pair of N210s, so each team could replicate the radio hardware locally, just not the execution environment. For the adversarial matches, 2 teams went head-to-head in a shared channel and were scored based on the number of packets they delivered. So you would be incentivized to transmit all of your packets as quickly as possible, but do so in such a way that prevents your competitor from transmitting theirs. The cooperative matches, on the other hand, were run with 3 teams in the same channel, but your scoring was an aggregate of the performance of all 3 teams in the match. So this meant that you were incentivized to transmit your packets as fast as you could, but also not interfere with your competitors. So we have these 2 scoring functions where the scoring is strictly based on your interaction with your radio and a competing radio or radios. But as a competitor, you only have access to your own code, your own radio. You have no way to run your competitors' radios locally. And so because of this, there was kind of an opaque and slow iteration cycle because you weren't able to have that tight feedback loop of observing your radio compared to someone else's, making changes and iterating quickly. And so because of this, I feel that there weren't a lot of technological breakthroughs with the First Spectrum Challenge, but it was very successful, in my opinion, at getting a community built around SDR. I've, since starting this, spent the last 7-8 years of my life really interested in SDR. I've worked now professionally with people from several of the other teams in the First Spectrum Challenge. And I think from that standpoint, DARPA did an excellent job of fostering a lot of interest in this space. And this led to going on to the Spectrum Collaboration Challenge, which Matt will now talk you through.
Thanks, Mark. Following the success of the original Spectrum Challenge, DARPA sought to focus their objectives on collaborative radio performance with the Spectrum Collaboration Challenge. Additionally, DARPA designated this competition as a grand challenge, meaning it had a much larger scope and cash incentives for success. To elaborate on collaborative performance, this meant that competitors were tasked with building high-performance radios that were still good neighbors to their peers. Performance was evaluated by pitting competitors against not only each other, but also against environmental conditions and incumbent radios. Competitors would score points for delivering traffic, but only if doing so did not interfere with the operation of other networks also operating in the shared spectrum. This, in essence, was a competition about cognitive radio, radios that could sense and adapt to the RF environment to improve the performance of all spectrum tenants. Additionally, there was a significant machine learning and artificial intelligence angle to the design of this competition. DARPA wanted to show that radios could make machine timescale decisions about optimal spectrum usage. This as opposed to human timescale spectrum licenses that are currently administered, that last years in most cases. To support this, DARPA commissioned a powerful RF testbed to host the competition. Dubbed the Coliseum, it was a supercomputer driving USRP X310s, running match orchestration software to coordinate loading competitor-provided software in various match configurations. While the competition was successful and enormously fun, there were a few key drawbacks that I'll briefly comment on to illustrate some of the key takeaways that informed the decision of the radio resilience competition. First, the game structure was very complicated. At its core, it was a multi-agent problem, since teams controlled many nodes, but also had to coordinate with other nodes that they did not control. However, the competition also had a complicated and somewhat opaque scoring system, which meant that it was difficult to source ground truth data to make real-time decisions off of. Competitors had to rely on self-attested performance metrics provided by other competitor networks. In general, competitors had myriad variables to optimize for. However, at the end of the day, raw radio performance was the biggest factor in determining the team's overall performance in the competition. Additionally, while the Coliseum infrastructure was impressive, it came with some big drawbacks as well. First, while the Coliseum was blazingly fast in matches, with powerful server CPUs and NVIDIA AI processors processing GPUs running competitor code, the surrounding infrastructure was slow. Matches required 12.5 minutes of setup and several minutes of teardown time, plus the time spent on the simulation itself. Teams also had to share this resource, which added to the queue even more. This meant that each test period took in excess of 30 minutes in a best case scenario. However, in the run-up to the actual tournaments, that could grow to actually span several hours. Second, the Coliseum was hard to develop for. We estimate that 80% of our development work went into plumbing, to support the Coliseum, and other compliance checks, rather than into engineering our algorithms. Lastly, the Coliseum was buggy. Of note, the channel emulator had a critical design flaw that would cause it to saturate, and that needed to be explicitly engineered around. In spite of all this, the Coliseum was an amazing piece of engineering. It lives on as a wireless research testbed under the supervision of Northeastern University, thanks to funding from DARPA and the National Science Foundation. I want to briefly give a shout out to and thank the DARPA Systems Engineering and Technical Support staff, who were amazing throughout every step of the competition, and to all the engineers that helped build the Coliseum. The Spectrum Collaboration Challenge was a huge opportunity for Mark and me. We were lucky to have been able to compete. We learned a ton from it, and we are excited to put some of these key takeaways to work as we embark on running the Radio Resilience competition. To briefly summarize our lessons learned from the Spectrum Collaboration Challenge, I think the big key takeaway was that the SC2 showed that the PHY is not a solved problem. Because so many teams' performance was bounded based on how performant their overall radio design was, that really illustrated that the PHY was a really key variable that still merits further exploration. Additionally, by having such a multivariate scoring system, it showed that with too many variables, you oftentimes don't wind up solving for any one problem completely. Additionally, while DARPA's infrastructure was enormously empowering to an independent and self-funded team like Mark and mine was, it in many ways was not sufficient to push the envelope forward in this domain. We believe that tight testing loops are critical to ensuring rapid progress, and fully reproducible testing environments are a good way to accelerate competitor progress in this regard by removing bottlenecks on shared centralized infrastructure. Having discussed our analysis of DARPA's prior software-defined radio challenges, we will now switch gears to discuss the overall design of the Radio Resilience competition. Let's begin with our key objective: to improve the state-of-the-art of resilient radio links. To that end, we designed the competition with these tenets in mind. We want to focus on the physical layer and to design simple rules that incentivize innovation explicitly to that purpose. Additionally, we assert that radio links must be reliable above all else. Thus, our scoring system requires exactly that links be reliable, with no drop packets or duplicate packets to score well. We wanted to provide the lowest barrier to entry possible in terms of cost, access, and complexity. We want to attract a broad swath of competitors, and we want them to be spending their effort on algorithms that advance the state of the art rather than software to support our bespoke infrastructure. Lastly, we want to enable a tight testing loop for rapid experimentation and iteration. Thus, we designed our competition to run entirely in simulation with no RF hardware required. We realized this with a collection of GNU Radio-based microservices that are orchestrated via Docker Compose. Competitors provide their radio software as a Docker container that emits and receives IQ over zero MQ sockets. And lastly, while the competition itself will run in the cloud, the simulator is fully open source and can be run locally for fast iteration by competitors during development. Rather than boring you with a detailed discussion of the rules, I'll instead provide a brief overview of our scoring methodology and will direct you to our website, radioresilience.com, for all the full details. Here's a high-level description of how matches work. Our traffic marshal container will send one of your two radio containers a series of JSON web tokens over 0 MQ. The radio container receiving the 0 MQ stream will modulate and send its contents over the virtual air to your other radio container. Upon receiving that radio container will then submit those JWTs back to the marshal container to be scored. Because we wish to emphasize reliability, these JWTs must be submitted sequentially to score. Because we wish radios to operate as a reliable tunnel, dropped or repeated packets are penalized harshly. As long as you submit packets sequentially, your score is equal to the sequence number of the highest submitted packet. Skip one, however, and the scoring stops. As mentioned, the competition is powered by Docker-based microservices orchestrated by Docker Compose. Each microservice that has a signal processing function fulfills said function through either GNU Radio or Liquid DSP. Docker Compose configures the infrastructure's networking such that the competitor containers can only communicate with each other via the RF channel emulator. No opening a socket and passing raw ZMQ data directly because it will not be routable. Lastly, and I want to emphasize this last point because I think it's really exciting, we are providing a fully working environment in base competitor image. This means that out of the box, you will have a working submission-ready image. We're doing this because we want you to be spending your time on building the algorithms that matter, rather than on supporting our bespoke infrastructure. Now, I'll hand things over to Mark for a walkthrough of the microservice architecture.
Thanks, Matt. So as Matt mentioned, the infrastructure that we built is based on a series of Docker microservices that are orchestrated using Docker Compose. And what this means is, as a competitor, you can clone our repository, run a script, and the entire process of spinning up the match execution containers and environment and running the match is all automated. Each container has an installation of GNU Radio as well as Liquid DSP. And the IQ and packets pass between containers over IP using 0-1-key. And so we've leveraged the virtual network isolation capability within Docker and Docker Compose to constrain that such that containers can only talk to other containers that they're supposed to. So the blue radio can't directly listen to what IQ is generated by the red radio can't directly transmit IQ to the blue radio, and so forth. The IQ all has to go through the muxer or channel emulator. And then we provide a fully functional competitor radio and execution environment. So we've included a packet transceiver that you can use and submit immediately to the competition if you want it. So here we have the blue radio container. And the blue radio is the set of radios that each competitor controls. So we have a Docker file for building this container. And again, this is populated with an example competitor implementation that you can customize as you see fit, or just build a new container from scratch. We have paths here for the Docker file, as well as some scripts and example of GNU Radio flow graphs. And we have the path for gr-RIRC syn, which is a GNU Radio module that we built for the competition. And this includes the muxer as well as a wrapper on Liquid DSP. So you can use Liquid's packet transceiver from within GNU Radio. And I want to comment that I'm a really big fan of Liquid DSP. And I think it's a great type of library to use for this. The reason is that it supports a wide variety of modulation and error correcting schemes. And so you can easily switch back and forth between different file configurations that might have a non-trivial impact on your performance in the face of interference. The only downside to Liquid DSP is that it is not built as an optimized real-time packet radio engine. So the version of Liquid that we have in the containers, we've applied a number of patches to leverage some of the Volt kernels where feasible to improve performance in the receive chain. Now we have the red container. And this is the container which is generating that intentional or unintentional interference signal. Now in Spectrum Collaboration Challenge, this would be called one of the incumbent radios or incumbent jammers. And in SE2, there was this obligation to characterize the behavior of the incumbent radios and protect them. So the teams competing in SE2 would be able to lose points if they don't successfully protect the incumbent. In RIRC, this is not the case. The incumbent is there to lower your score, but not to do anything else. So you have no obligation to protect the incumbent or otherwise alter your behavior in response to it, except to the extent that you need to change your behavior to improve your packet delivery. Then we have the channel emulator. And right now, this is a relatively simple channel emulator. It takes IQ in from the blue and red flow graphs. It mixes them, adds them together, and then adds in some noise to form a channel. And then that IQ goes back out to both blue radios and the red radio. And then optionally, the host can be listening with the example baudline script to observe the IQ that's going on when you're running the match. And this is useful for debugging purposes. It's the same base image as the other infrastructure controlled nodes and is essentially the same image as the competitor nodes.
The last microservice to discuss is the traffic marshal. The traffic marshal, also referred to as the scoring container, is responsible for generating scoring traffic and calculating your score based on what is received over the air. As discussed, the data type sent is a series of sequential JWTs. The JWTs contain sequence numbers and pseudo-random data, but also a signature to ensure that they can't be forged. As discussed, packets must be delivered back to the traffic marshal exactly as sent. The same data in the same sequence with no duplicates. In essence, your radio must be a reliable tunnel to score well. Well, enough about the infrastructure. Let's talk about how to get started. From the beginning, we have sought to make competing in the radio resilience competition super easy. To get started, you just need to follow these steps. First, head over to our website and get registered. Once you're signed up, clone our simulator infrastructure to get started locally. Now, to walk you through the rest of the steps, I'll hand you over to Mark, who will show you a demo showcasing just how easy it is to get started competing in the radio resilience competition.
Okay, let's see what it looks like in action. So we're going to start here by opening up our flow graph in Vim for the Blue 1 radio and resetting it such that it's using no error correction. So FEC 1 and 2 set to 1 means no error correction. And then modulation set to 2 means we are using QPSK. And we'll go out here and run the run headless.sh script. This is starting the containers, which we previously built. The containers are coming online. The match is starting. We can see already that we have errors printed out here saying expecting 7 received or got n. So this tells us that the scoring server is expecting packet 7, but it got something higher than that. And sequential delivery is required for increasing scoring. So because we dropped a packet early on, we're going to have a pretty bad score of only 6. So now we're going to open that flow graph again and change the FEC 1 value from a 1 to a 4. And this is going to add a 4-7 ham encoding to these packets. And the hope is that we'll have a higher rate of delivery. So we're running the match again. We have the container starting. We have the application code ready on Blue 1 and 2 in red and the muxer, and here the match is starting. Now we can see we've already surpassed the previous score of 7 because we have sequential packets getting delivered due to the ham encoding. Now we can see with that very simple change to the flow graph, we're able to have a marked improvement to our delivery rate. That gives us a score of 135. There we have it.
Now, to comment briefly on the competition itself. Effective immediately, daily matches will be run on our hosted simulator leading up to the competition. As soon as you submit a container image to our repository, you will be registered to compete. Daily scores will be published to the radioresilience.com leaderboard page, which you can find by visiting www.radioresilience.com and clicking the appropriate tab. The competition itself will take place on the weekend of October 3rd. Timeline and format to follow. Thanks for your time today and for your enthusiasm. We hope that this is just the beginning. We're looking forward to a successful competition, and assuming everything goes well, we will host additional competitions and follow-on activities to build on our shared success. Thanks very much, and we look forward to hosting you in the Radio Resilience competition. Visit radioresilience.com to get registered and to get started.
Great. Hello, we're going to be starting up the main track again in just 2-3 minutes here, as I saw from the countdown timer. I wanted to say thanks everyone for your patience again this morning. Things have been running pretty smoothly for the last couple of hours. The one issue which we have noticed is that if you were able to register for the workshops kind of in the last 2-3 days, a few of the emails appear to have not gotten through. So especially if you're signed up for the workshop coming up in just a few minutes, the Writing Python blocks, please do check your email and double check your ticket information, the actual PDF of your ticket, and that should have the link for joining the session. If you don't see that and you think you should be in on the session, please do drop us a note in the help channel and we'll do our best to get you in. Thanks so much for all of your understanding through this, and we're looking forward to the rest of the conference and hope that you enjoy this upcoming talk. Thanks. Sorry, me again. I wanted to also mention that the Capture the Flag Challenge has been open since this morning, and we have, let me check the numbers, a huge number of people have already joined in. We have 63 people registered for the CTF. There are a whole stack of challenges. I don't know whether I'm supposed to divulge the actual number, but plenty to keep you busy for the rest of the week. And that's living in the CTF channel, which is titled, let me double check that, Deviations this year, the GNU Radio GRCon Capture the Flag Deviations channel. You can find that link in the participation guide. And we'll be getting updates throughout the week on how that goes. Thanks very much.
Steve Croft, an astronomer, astrophysicist, and educator, specializes in the interplay between black holes and their environments, in time domain and radio astronomy, and in the search for intelligent life beyond Earth. Extensive experience dealing with large datasets and scientific writing. He's enthusiastic about communicating astronomy to the general public and expanding educational access and equity. Please welcome Steve Croft.
I'm Steve Croft, and I'd like to tell you today about how GNU Radio can help us find ET. I'm jointly affiliated with the Berkeley SETI Research Center, which is based on the UC Berkeley campus, and with the SETI Institute just across the bay in Mountain View, California. The motivation here is that in the last few decades, we've discovered that planets are common. Indeed, Earth-like planets are common in the universe. There are hundreds of billions of stars in our galaxy, and about 1 in 5 of them has a potentially habitable planet around it. So to paraphrase Enrico Fermi and his so-called paradox, where is everybody? If there's all this real estate out there, then why haven't we seen any signs of life? There are 3 main ways that we can search for life. One is direct in situ sampling, so we can go to Mars with instruments like those on the Curiosity rover. We can directly sample the dirt that's there, and we can see if there's signs of biology that's there now or has been there at some point in the past. We can also do remote sensing for so-called biosignatures. Now, this is really challenging. Imaging planets going around other stars is very challenging, and getting spectroscopic information where you could see signs of oxygen or water vapor or maybe even vegetation in the atmosphere is really hard. It's going to be out of reach, really, for even the next generation of telescopes like the James Webb Space Telescope. And there's proposed successors to Webb, LUVOIR or HabEx. So there'll be a selection made by NASA in 2021 for these missions to launch around 2035. And you can see the mirror sizes down there in the bottom right. It's really going to take a big leap in technology in order to be able to detect biosignatures around even a handful of nearby stars. So we have one example here on Earth of an inhabited planet, and here on Earth, biology has also developed technology, and of course, radio communications technology, the topic of this meeting, as many of you are aware, is detectable at interstellar distances under the right conditions if you have a large antenna. So these so-called technosignatures as a proxy for intelligence are the basis of SETI searches, these searches for extraterrestrial intelligence. Not limited to just radio, we could look for powerful lasers, we could look for evidence of large structures that have been built in orbit around stars, which might modify the light of the stars as they go around. But really the traditional SETI searches are in the radio, and that's still sort of the bread and butter. We're still just beginning to explore the breadth of the radio spectrum at different frequencies to build instruments that are sensitive enough to pick up technologies that are sort of Earth level, leakage radiation from technologies like we have here on Earth, or intentional transmissions that have been beamed in our direction. The largest SETI search underway today is the Breakthrough Listen project. And I'm the project scientist for Breakthrough Listen on the Green Bank Telescope. You can see here a picture of the Green Bank Telescope with the Breakthrough Listen chief engineer, Dave McMahon, in the foreground. The collecting area of GBT is the same as 2 football fields. It's the largest movable dish that is anywhere on the planet. And it really is amazingly sensitive. And the Breakthrough Listen project has 20% of the time on the GBT to observe stars, actually to observe other galaxies, to observe a variety of targets of interest. And so we're doing a SETI search, the likes of which has not been done before. We're also putting instruments on other telescopes around the world, optical and radio in different places. We've got a project with the Meerkat Telescope in South Africa, which is the precursor telescope for the Square Kilometre Array. And then the SETI Institute also has engagements with the Very Large Array in New Mexico to put new instruments on the VLA. That's the telescope that if you've seen the movie Contact, you'll have seen the SETI searches that were done there fictionally that are now becoming a reality. And these are sort of setting the ground for the next generation Very Large Array in the US and the Square Kilometre Array in South Africa and Australia that are really going to help transform the field. The instruments that we have, including those that are already at the Green Bank Telescope, really operate on the same principle as GNU Radio. We digitize the raw voltages or IQ signals. We do a fast Fourier transform to form a spectrogram, and then we look for signals of interest. In fact, we actually shipped RTL SDRs to all of our interns who are working with us remotely this summer, but we've also done in-person demos with GNU Radio that really illustrate the concepts of forming spectrograms and then actually detecting signals, classifying the signals, and then doing the kind of searches that we want to do. The instrument at the Green Bank Telescope is a lot more scaled up than those little RTL SDRs. We have 12 gigahertz of instantaneous bandwidth with GBT. You're just seeing half of the GBT instrument here in the image on the left. And we get basically billions of radio channels at a time. The channel width can go down as fine as 3 hertz. So that generates a lot of data. We have 8 petabytes of storage on site, 400 teraflops of compute. And there's 64 of these compute nodes, these individual servers that you see in the racks here that are digitizing, each of them 750 megabytes per second. We're observing about 5 hours a day, 20% of the time on the GBT. And so we're generating hundreds of terabytes per day of raw voltage data. And we've been doing that since the project began in the beginning of 2016. We can't archive all of that data, so we have to reduce that to dynamic spectra at basically about 2% of the original data volume. Just a few hundred gigabytes per hour. This is the output from one of those compute nodes, you're seeing 187.5 megahertz of bandwidth from GBT over 5 minutes in time. The vertical stripes here that you're seeing are due to the polyphase filter bank that we use to generate the spectrograms. And you're seeing some signals here, but the question is, are these signals from our own technology, or should we be interested in them as potential technosignatures? Well, as you're all aware, there's a lot of signals that are out there that are all across the radio spectrum from human-generated technology. And so this is the haystack in which we have to look for the needle of the technosignature that we're searching for. So how do we do that? Well, we can point the telescope somewhere else and see if it looks different. Here is a pointing that is off the original star that we were looking at. And in this graphic here, using the Stellarium software, you can see just an example that I've cooked up here. The telescope pointed at the star Vega in the close to the center of the image here. And then as you'll see in the animation, basically we're looking at Vega for 5 minutes. We move to a neighboring star for 5 minutes, then back to the original target, then to another neighboring star, back to the original target, and then off to another neighboring star. And you'll see that if we now shift to a different star in another part of the sky, close to the geosync belt here, that even though the satellites here in the sky are stationary in position with respect to the horizon, because the star is moving relative to the horizon, this on-off method enables us to see where the signals are uniquely coming from the direction of the star by comparing to the off observations, even when there's potentially satellites passing through the telescope beam. So here's some examples again of real data from the telescope. The on observations where we were pointed at a particular star are in the top row, the off observations in the bottom row. And so essentially what this amounts to is we're looking for signals that are in the top row of images where we pointed at the target, that are absent in the bottom row. And you can see just by eye here, there are no convincing examples of signals that are just in the top row. There's certainly some that appear in the top and bottom, including, if you look in the right two panels, some signals around 2400 megahertz, 2.4 gigahertz. This is probably a Wi-Fi signal from somebody that hasn't turned off their phone Wi-Fi when they're at the telescope. So essentially what we want to be able to do is to kind of draw boxes around signals in images like this, to recognize and classify the signals that are in there, and to look for anomalous signals. In the sort of cartoon here, the ET signals appearing in the upper row, and then to tease those out and to follow them up, basically, if there are signals that are interesting in that respect. If you want to have a play around with some of the data, we have about 2 petabytes of public data, in addition to several more petabytes that are just stored on disk at the telescopes. There's some observations of the Voyager spacecraft. So even though Voyager is about 20 billion kilometers from Earth, we can pick it up, both the carrier and data signals, loud and clear with the Green Bank telescope. And you can go and work through some Jupyter Notebook tutorials. You can look at the Open Data Archive, and you can find data there and have a look at it yourself. There's also some GBT data that's in SIG-MF format, which you can read into GNU Radio directly, and Derek Kozel has some nice tutorials. We're going to be working through this in the workshop that we're doing later in the conference, where we can actually find the Voyager signal using the GNU Radio flow graphs here. And here it is. The big spike in the middle is the DC spike that you see in the bottom left, but you can see faintly around sort of 2200 or so on the 22,000 or so on the x-axis here. That's the Voyager carrier and the 2 data channels there. So as I mentioned, Breakthrough Listen has about 20% of the time on the GBT. Here's a little snapshot of the GBT schedule. But SETI scientists also have 100% of the time on the Allen telescope array. And if you want to try engineering experiments, this is a really good place to do it. And my colleague Alex is going to tell us more about the ATA in just a minute. We have some undergraduate internships. I mentioned interns working with us during the summer. If any of you are undergrads and are interested in working with us, we'll be opening applications in December, closing in February for next summer. And you can also watch our social media for any job announcements that are coming up. So before I hand over to Alex, I'd like to just point you to, again, our social media, to some resources where you can work through some of our data in Jupyter Notebooks. And we're really excited to be partnering more closely with GNU Radio. I hope there's going to be a lot more collaboration in future, getting our data into GNU Radio using the tools and techniques in GNU Radio to find signals of interest. Thanks very much.
Hello, my name is Alexander Pollack. I'm the Science and Engineering Operation Manager of the Allen Telescope Array. And today I'm going to talk about the development for radio technosignature searches using GNU Radio. So the first part of the talk, I'm going to give you an overview of the Allen Telescope Array, or the ATA, how the telescope looks like, how many antennas we have, the infrastructure, and the research which we're doing with that telescope. And in the second part, I'm going into detail on the community GNU Radio hardware, which we installed a couple of months ago, and which purpose is to kind of allow the GNU Radio community to take data and use the telescope in the GNU Radio environment. So to give you an overview, so the Allen Telescope Array is located in the Lassen National Forest at the Head Creek Radio Observatory, which is about 5 hours north from San Francisco, depending on Bay Area traffic. And if you look at Google Maps, you can see a nice area shot of it where you can see all of those dots. Those are the 42 individual antennas, which are scattered around the main site. And then we have the building, which has a green roof here. That is a central signal processing building. So all of those antennas are connected via an analog fiber link into that building here, where then the digital signal processing is located. On top of that, we also have a small visitor center in there where kind of people can come in and get some information about radio astronomy and the search for extraterrestrial intelligence. So the other buildings which you can see here are mainly kind of labs where we do maintenance work on the feeds and on the antennas and machinery. So if we look at the antennas itself, we have 42 antennas installed. And each of those antennas has 6.1 meter diameter, so that's the primary reflector, and then for 2.4 meter secondary reflector. So the purpose of those reflectors is to have a large collecting area and then focus the waves at the focus point in the center here, where we then deploy our feed, which detects the signal and then sends it to the central signal processing room via the fiber link. The nice thing about the ATA is that it's a very flexible instrument. So you can use all of the 42 antennas together to look at one object. So you get the most sensitivity, the most collecting area. But if you say you want to kind of observe more area, you can also, or multiple objects, you can also group them together in subarrays and then point at different objects of interest at the same time and do observation that way. So it is very flexible. You can do an observation with a single antenna and up to the 42 antennas. And as I said earlier, all of the signals which are collected by the antennas are sent via an analog fiber link into the signal processing room. So if we look at the heart of the antenna, we have the Antonio feed, which is something you not really see very often in those types of antennas. It's a log periodic design. And the idea is of the log periodic design that low frequencies are coupled in at a quarter wavelength here, the low where the antenna or the feed is bigger, and the higher frequencies are coupled in on the top where it's smaller. So pretty much the operational frequency band of those antennas or feeds just depends on the size of that feed here. And in our design, which we deploy, it works from 1 gigahertz to 15 gigahertz, whereas the fiber link at the moment just supports 12 gigahertz and is in the process of being upgraded also to 15 gigahertz. So you have to imagine all of those parts, that copper part here is in vacuum. So we have what you can see over here, a glass cylinder which holds high vacuum. And then we have a cryo cooler which cools down that entire feed to about 80 Kelvin, which reduces noise and therefore improves the sensitivity. And as I said, kind of here, that one is a picture where you can see the feed installed in the focus point of the antenna and where it is in operation. To give you an overview of the overall kind of instrument on a very kind of top level basic design, we have our antenna, we have the Antonio feed, which is the conversion between the radio waves traveling in free space to the radio waves traveling then on the optical fiber. And then the signal comes out in the central signal processing room. And here we have those radio frequency conversion boards where the yellow fibers, each of that pair is one antenna. So we have two polarization, one antenna. And then that conversion board allows you to look at 4 different tunings, which you have here with a 700 megahertz bandwidth within those 1 to 12 gigahertz. So you can select at the same time, for example, all of the same frequencies or kind of multiple frequencies, or we can have multiple instruments looking at the same frequency. So at the moment, there are 2 instruments which are deployed. One is a snap-based FPGA board, which we use for our observations. And the second one is the other USRPs, which we installed for GNU Radio, which we get into detail a bit more. Apart from kind of the overview of the whole system, we also do a lot of design work, modeling work. So what you can see here, for example, is an optical model of the antennas. So we have the entire ATA antenna as a model where we can then calculate what spillover we have, what the performance is. So if we install a feed or kind of different feeds, we can then make sure that it fits to the optics. We also have a full EM model or electromagnetic model of that feed, which we use, so we can optimize it and make sure that everything works up to spec. And then that is just some kind of examples of designs which we do in-house, especially for the ATA. Because we try to buy things off the shelf, but you can't do that all of the time because it's a very specialized instrument. So sometimes we have to do our own designs. So the other thing is kind of maintenance and repair and kind of, as I said, construction and manufacturing. So that is one of those signal processing boards where we have at the moment 12 of, which have kind of a 5 gigasample ADC or single polarization or dual polarization with, I think, 2.25 gigasample sampling rate in FPGA, and then a 10 gig Ethernet link where we stream out the data. So we build a kind of all of those, so what we can buy off the shelf, and then we kind of design the enclosure and make sure that things are reliable, as well as kind of something which you can see here, which is an analog conditioning board, which allows us to set the gain level correctly for whatever digital signal processing backend comes at the end. So from there, that is our existing backend. We kind of, let's have a look. This is our new digital signal processing backend, which we're developing at the moment, which is called a multi-mode digital backend. So the idea is very similar. We use an RF SOC to digitize up to 4 antennas, dual polarization, or pretty much 2 antennas, 4 tunings, if you want to take all of the tunings, and then we can stream out all of the data via 200 gig Ethernet link. And the idea there is, if you have channelized voltages, you can set up your digital signal processing or what you want to do with the channelized voltages, then at the end by subscribing compute nodes. So you can implement a correlation or a correlator, a baseband capture, beamforming, deep space modem. So you can implement that very flexible with such a design. And so we're in the process of designing a system which will take all of the 4 tunings for all of the 42 antennas and digitizes them and then sends them over 100 gig Ethernet backbone, which is quite interesting. From there on, from the development side back to what we're actually doing at the moment. So a lot of the part, what we want to do is observations and science. So we're spending some time doing fast radio burst observation. Fast radio bursts are very bright flashes in radio sky, which are very interesting in the scientific community at the moment. We do pulsar observations. So that is an example of what you can see here. That's a typical pulsar plot. And the peak here, which you see, the triple peak, is that pulsar which is detected with the ATA. And this is a 30-minute observation with 10 antennas with 700 megahertz bandwidth. And then finally, something which we're kind of working towards is having high resolution observations or spectral observations, which are so-called kind of the SETI observations. But before we get to that point, we want to make sure that the system works, and we've done kind of a lot of verification with known sources. And then if we understand the system very well and we know it works reliable, then we start kind of at the end of the year a SETI observation campaign. So that is so far the overview of the ATA. Now I'm kind of just want to talk a bit about the GNU Radio side. So we had last year, when the world was still okay, in May, a hackathon where 30 plus people came to the ATA and developed software and were using the instrument for experiments and for software development. So that was the point where the GNU Radio ATA came up with, which was the first attempt to kind of use the ATA within the GNU Radio environment. And from that onward, we had collaborations, for example, with a company called DeepSig, which is doing signal detection and classification using deep learning. And we set up an antenna on the roof here on the main signal processing building, which is monitoring RFI, or radio frequency interference. Because our antennas are so sensitive, we need to make sure that if a visitor comes or if there's any kind of RFI source like a walkie-talkie close by, that we can identify such sources and get information of it, so we can find them and eliminate them so they're not interfering with our observations. So that is something which we are kind of quite excited about. And so that was the first step where we installed it. And then a couple of months ago, we were kind of quite happy to say that we bought two USRPs, an N321 and an N320, which you can see down here, the pictures, and a server which allows us to use the ATA within the GNU Radio environment. So I just give you a brief overview of the system diagram for the GNU Radio backend. We have our antennas here, which have the 1 to 12 gigahertz fiber link into the central signal processing room. And here we have our 4 tunings. And out of those 4 tunings, one tuning is connected to a switch matrix, which you can see down here, the picture. And that switch matrix pretty much allows you to select on the first one between 16 different antennas, which one you want to have routed through the USRP. And then we have a 200 megahertz bandpass filter in. So the USRPs at the moment have effectively 200 megahertz bandwidth. And then the second one has 8 antennas connected to it. So you can pretty much choose between 24 antennas with 2 USRPs, which one you want to kind of use for observation. And the output of those is then a 2 times 10 gig link, which goes into a 40 gig switch. And then we have our GNU Radio server, which you have the picture down here, where GNU Radio Companion is installed and which is used to control the ATA then. And if you collect a lot of data and if that machine is full, we also have 100 terabyte storage available where you can kind of store data then. So that is kind of quite exciting, having those hardware installed, hooked up to the antennas, and a GNU Radio library, which allows you to use them. So for kind of pretty much my summary slide, the interface into the ATA, we have either a VPN connection or an SSH gateway for people who are interested on kind of coming in from the outside world. We have the full control over the array via GNU Radio and the GR88 blocks. And in case that the array is used by us and you can't have full access for it, the USRPs are hooked up anyway, and you can use it as a commensal mode where you can pretty much acquire data from the antennas 24/7 and get the metadata, so you know where they're pointing and you can collect all of the data. And then, as I said earlier, you can pretty much very flexible connect to which or choose an antenna which you want to use. So if you have a favorite antenna which you think works best, you can always pick that one. The code has been developed by an REU student, Ellie White, and she was giving a presentation here as well about the software in particular and demonstrating it, and also has a poster about that software. And the software can be accessed at GitHub, SETI at HCRO, GRATA. And if you want to know more about the ATA, there's on the SETI homepage are the ATA memos. And the first one of the ATA memo series is an interface document which tells you exactly where the ATA is located, what the frequency ranges are, what the IF frequency is, what the clock distribution is, and everything. And then also kind of 95 more design documents which you can go through. And if you're interested in using the ATA and kind of working with us on developing GNU Radio with the ATA, you can get in contact either with kind of Derek Kosel or with me, and we can set you up with an account for it. And with that, I'm kind of want to say thank you and bye.
Hello, GNU Radio Conference. Hayden Nelson here with NI and Ettus Research. Good to virtually see you, and welcome to my coronavirus software-defined radio demo bunker here in Austin, Texas, or as I like to call it, my home office. Really, unfortunate we don't get to be there in person, but we're really excited to be back at GNU Radio Conference. This is the 10th year, and actually this is the 10th year since NI acquired Ettus Research, which is also exciting. And so we're excited to be here again virtually, if you will, to connect with you and learn about, look at the great technical program that's going to be had, and and virtually show us some cool demos. I've set up all my sweet SDR gear here behind me, so I don't normally keep it like this. So today, what I wanted to discuss with y'all, or share with you, I wanted to share a few kind of updates from the Ettus Research side, and bring in some of our new faces and some known faces from the software-defined radio R&D team to talk about some of the latest enhancements to the USRP hardware driver that we recently released. So, well, here, let me start by sharing my screen and talking through a few updates with the Ettus Research side, and then we'll bring in some of the R&D folks. Here we go. Hit share. All right, great. So today, I titled this talk "A Conversation with the Software-Defined Radio R&D Folks," but couldn't get through this without giving y'all a quick update on some of the things that we've been working on to benefit the SDR community out there. And one thing you will notice on this slide is this this little green thing down here. And so, I won't spend much time here, but you may have noticed that National Instruments went through a major kind of corporate, identity change, I guess, if you will. And people may have already known National Instruments as NI, and we've kind of renamed the company officially to NI. And that was really around the notion that National, we sell more than just in the United States, and Instruments, we sell more than just instruments. Our USRP devices is a really good example of that. They're software-defined radios, not instruments. And so it's kind of an acknowledgement of it, the companies needed to evolve the way we're perceived and some of those aspects. Not probably that interesting to the average engineer, but that's kind of the reasons. The cool thing is it's green. So I actually was really excited to see the choice of green, because everyone kind of knows Ettus Research has used the green colors. So, NI finally came to its senses and picked the right colors, I guess, so to speak. Anyway, so this year at GNU Radio Conference, we have the NI and Ettus Research team has a couple new faces and a couple known faces and several good technical talks. We're really proud to have been a major contributor to this conference since its first one in 2011, and always trying to contribute to the technical work that is this content that is attached to this conference. And it's always a thing we're really proud of is being able to add back to the community with helping people building their wireless applications and share some of the great work around SDR. So Tuesday, I encourage you to, we all know Martin Brown. He's going to be talking about some of the updates to GNU Radio 3.9, the de-swigification and how they're removing this, some tooling from GNU Radio 3.9. A new face to the group is actually a gentleman named Aaron Räisänen, who is a principal SDR software architect. I've worked at NI for about 10 years, and when I started, Aaron Räisänen was one of the senior software guys at that point at NI, and so he's been in software development for many years. He's a phenomenal software engineer, and we'll be sharing some of the work that he's been doing with the Python API in connection to the RF network on chip framework. And then Martin Brown will return on Thursday, talking about some aspects, connecting the analog world to the digital world in his talk on how strong is my SDR signal. And Abhay Samant is our chief software engineer for our aerospace defense systems R&D team. Now kind of with that changes to NI, we've organized into different industry business units, and we're investing a lot in defense technology, and SDR is a strong part of that, as well as some of the commercial wireless side. Abhay joins us from our aerospace and defense team, and he has a strong background in those applications. And of course, wouldn't be a GNU Radio conference without our known and loved workshops. So if you haven't already registered, we're starting these on Tuesday and on Friday. We're only doing the FPGA workshops this year, where we're going to be walking through how to use the RF NOC framework for you to, essentially build your wireless application using FPGA technology. And so we have a number of great experts coming in. On the right, a known face, Jonathan Penlam, who was one of the original RF NOC architects and is a known SDR expert. Aaron Räisänen, also on the software side. Wade Fife, who will be joining me here in a moment, is a principal SDR digital engineer. And this last picture here, I can kind of highlight it. We believe this is the best image representation for Anil Pandya that we have at Ettus Research. We believe it's very representative. It's what we could find, and so this is what we believe Anil Pandya looks like in the wild. And of course, he has his trusty USRP in his hand, as we expect him to always have in his hand. This image, courtesy of Alex Wiglinski from WPI. And so Neil will be joining us. And so one of the things this year we won't have is the GNU Radio workshops. And so if you guys any of you all came to Huntsville last year at GNU Radio Conference, we actually had to expand to have 2 additional sessions of the GNU Radio workshops for new users, because we had so much demand for people to learn, just getting started with GNU Radio and the USRP. So that's a very popular workshop. This year, we're only focusing on the FPGA version of that, so we are not conducting the USRP GNU Radio workshop. But fear not, we are. So if some of you may have remember me getting up on stage last year in Huntsville, and I showed you a picture of my Texas redneck truck where I bolted a USRP onto the roof rack, and was talking about how much fun I was hacking with my USRP out in the wild. I actually, through that process, I built some kind of introductory coursework. Well, we've taken some of that work, as well as the GNU Radio workshop that Neil has been executing at GNU Radio Conference for years, and built some digital on-demand modules. Now, we've hosted this on the NI learning platform, so you have to go to www.learn.ni.com/training, create a profile, log in, and search for using open source tools on USRP. And so this course is free. It's ready to work, stream today if you are a new user. It'll help you get started with setting up a system with a USRP. You'll also be able to get started using GNU Radio, as well as do some basic SDR applications. Now, there are a number of really good tutorial tools on GNURadio.org that they've actually revamped this year. So if you are a new user, I recommend you look there. This is yet another resource for you. We do plan on expanding this course body of work by the end of the year, where we're going to be walking through building IP blocks and then connecting those to USRPs, and doing things like performance tuning of streaming application, as well as taking our FPGA training and making it more digital on demand. Here's hoping we'll be able to do these things in person in 2021, but this is really to try to help enable you, our customers, to continue to up-level your skills and get started if you're a new user in this time where we can't connect in person. So that's something we've done for the community, and it's all free at this point. And but you have to go to this web address to get access to this courseware, and it's ready today. So we're still selling radios. We're I don't have any brand new hardwares products to announce today. I guess B series, X series, E series, and N series. Last year we launched the N320, which you can see I have a 1 gig sample per second running on across 4 channels on some N series right here behind me. But one of the new radios is the RX310, and that's basically a repackaging of the X310. So if you have needs for like a rugged enclosure for an X310, that's something that you can reach out to us on. But the big thing is UHD 4.0, and so UHD 4.0 is released, and we're really excited about this. This was no small feat of engineering. Our R&D team has been working really hard on this. Martin came and talked about some of our plans around it last year. It's a major enhancement to the USRP hardware driver, with improvements all across the board. I can't remember how many lines of code it's changed, but we've improved performance, usability, flexibility, documentation, and like more than just the features, but like testing, like we've improved the quality of the code. And so with that, let me stop sharing my screen and get out of my marketing PowerPoint here. So you're probably all asleep at this point. Let's go ahead and bring in some of the folks from our software-defined radio R&D team. So if you gentlemen care to join us on the call here, we have some of our folks from R&D. Thank you all for joining me. So I guess what I wanted to start with today was was talking about some of the major updates and to the driver. I'll start with you, Wade. I know that you're a principal digital engineer on the SDR product line with how long have you been doing digital design again?
It's been since the beginning. So yeah, I'm a digital hardware engineer. My specialty is FPGA design, and I've been doing that since I graduated in 2003. Oh wow, yes. I used to be an FPGA designer at one point in my life, and then I ended up getting into the business and marketing, which is lose a lot of credibility there, I guess. Yeah, less fun.
Yeah, it's less fun, you know. It is less fun. You know, so on the FPGA side, so you know, one of the major changes to at UHD 4.0 was some enhancements we did to RF knock, and like some of the endpoints. You know, kind of what are some of the major things that you worked on, you know, in that development?
Yeah, so let me start just by giving a little quick introduction to RF knock for anybody that might not be familiar with it. But
Sure.
RF knock is our RF network on chip. So it's basically a framework that we've developed that allows you to do high throughput DSP applications on our USRPs. So one way to think of it is we provide all of the plumbing and the infrastructure for your USRP radio to work, and then you can add your own IP to that in order to enable your custom applications. And so as far as things that I've been working on, so again, my specialty is on the FPGA side. So I've been focused very much in the guts of the Verilog and the code that runs on the FPGA. So we've been using RF knock for a long time. So we've learned a lot, and we've been able to apply a lot of those lessons as we've kind of re-architected things in UHD 4.0 for an improved experience. So some of the things we wanted to do was scale the total system bandwidth that we have available. So you mentioned the N320 that was introduced last year, 250 megasamples per second. And so with a product like that, we're kind of starting to feel constrained by the current architecture. So we've actually wanted to improve things so that we can go well beyond 250 megasamples per second, beyond a gigahertz per channel is kind of what we're looking at. So, and I can talk a little bit about how we're able to achieve that. We also wanted to be able to scale the number of RF knock DSP processing blocks that we can have on a single FPGA. So we've made some changes to allow for that. And we also wanted the user to be able to have more trade-offs, right? To be able to trade off things like throughput versus latency, or flexibility versus area, so that they can make educated design decisions to optimize the FPGA. Because you want to get as much out of that FPGA as you can, because it's kind of a fixed resource. And also we wanted to improve the customer experience. So a lot of work has gone into tooling improvements and making it easier to create your own IP blocks to put inside the FPGA.
Yeah, because I remember was there any changes to because we still have the concept of, you know, within RF network on chip, it's this kind of infrastructure framework where there's like this network crossbar. So it's, and I recall, like in the 3.0 version, it had a limitation of 16 blocks. You know, that's somewhat has a higher bound now at this point.
Yes, so that's specifically one of the things we wanted to address. So in previous generation of RF knock, all of your blocks would connect to this crossbar, and each block would have a 64-bit port that connects to that crossbar. So you can imagine, first of all, that port, that's going to be a bottleneck at some point. You know, eventually you get to the point where 64 bits is just not enough. And we also had problems where if you had multiple channels, then those multiple channels in a block would share that 64 bits bandwidth. And so one of the things we did in UHD 4.0 is to make the width of the port of each RF knock block configurable. So instead of 64 bits, you can make it 256 bits, or up to 512 bits is what we currently plan to support, which gives you a tremendous amount of bandwidth. On top of that, you're not limited to having a single port. So if you have multiple channels, you can actually have a separate port per channel. So each channel can have its own dedicated bandwidth, which is great. So now back to the crossbar that you mentioned. We want to be able to fit more blocks. And so what we did is we introduced this concept of static routing, because what we found is when you basically when you first initialize the USRP, you set up the routes in that crossbar that connect one block to the next block to the next block. And what we found is that most people, they do that configuration once, and then the routes stay the same for the duration of the application. So instead of putting all of that traffic through the crossbar, what we did is we created a static section where you can actually connect the blocks end to end without going through the crossbar. So that reduces the requirements for the crossbar and reduces the number of blocks and things that need to actually connect to it. So on top of that, there's some additional benefits to removing things from the crossbar. If you have the blocks connected directly to each other, you no longer have the need for all of the buffering that currently existed in our RF knock blocks. So you can actually pull out a lot of that buffering, that memory, and a lot of the logic that implements the RF knock communication protocol and flow control. We can pull all of that out of each RF knock block and then put that into a separate block that we call the stream endpoint. And so now all of your blocks can be connected directly to each other without any of that logic in between them. And only at the end of the DSB chain do we need this streaming endpoint that has all the buffering and implements the high-level flow control for communication on the network.
So presumably that could have benefits for, like, obviously bandwidth, less logic in the FPGA in certain instances, probably. It's a
yes.
FPGAs are a finicky animal. You pull one here and something else, becomes another constraint, and maybe even latency, because I know like certain applications, latency is something that is really critical in like certain wireless protocols and like radar applications, things of this nature.
Yeah, specifically to add to that, in terms of latency, so another change that we actually made was to separate the data paths and the control paths in the FPGA. So previously, all of them, let me step back and define what I mean by data path and control path. So the data path is the RF data samples for your application, just the RF data. By control, what I mean is the register reads and writes to the RF knock blocks to configure them or to control their behavior or check on their status, those kinds of things. And previously that traffic was over the same channels. So your control traffic would actually eat away from your data throughput slightly. And that the data traffic could actually affect the determinism and the latency of your control traffic. So now those two paths have been separated. So you can actually have control traffic moving around on the FPGA completely independent of the data flow, and which actually opens up some really interesting applications where, consider, for example, you have an RF knock block that's actually controlling or tuning another RF knock block in real time. So this architecture allows you to have a really tight control loop between those RF knock blocks without being affected by the actual data that's flowing between them.
Interesting. I can think of like applications of like avoiding interference and tuning things around, in real time. It'd be kind of interesting.
Yeah.
Well, yeah, no, that sounds cool. I'm excited to see what people in the community will use some of these new enhancements for. That's one of the cool thing about our customers. They was building something really interesting. So, but I mean, one of the things was the bandwidth enhancements, and that to me is streaming, and that's been a major request from a lot of customers is like streaming performance. Like a lot of times, pulling data onto the FPGA and doing real-time signal processing, but oftentimes people want to move that data to a host machine and on the CPU side do some processing, and that's really about kind of streaming. So I'll bring Ciro. You're a long time NI, or actually I was at NI, started 10 years ago and sat right next to you for whenever I was a software engineer, and so you've been at NI for what, like 20 plus years, was it?
Yeah, that's right. It's 21 years now as a software engineer.
Okay, well,
a lot of those years in RF instruments, both RF tests and now SDR.
Okay. Yeah, it's we're excited to have guys of your longtime experience on the SDR R&D team, and I know that you worked a lot on the host side streaming architectures for UHD 4.0. What were some of the enhancements that you worked on and you think customers will like to hear about, I guess?
Yeah, for 4.0, we basically rewrote most of the streaming paths there in UHD for the devices that support RF knock. And the primary driver for that was obviously getting more bandwidth. Also, some of the changes that Wade talked about require some of the changes that we were making, like separating the control and data paths. That was also beneficial, I think, because the old streamer code had become a little bit hard to maintain and understand. So besides rewriting it and kind of looking for all the different places where we had unnecessary overhead, like removing, trying to minimize the number of virtual function calls, for example, try to remove the use of shared pointers in that code path, things like that. We also made a number of architectural changes that made our performance better. Our packet format is leaner and faster for us to decode. We also moved, for example, in streaming applications where you utilize multiple threads, we moved the flow control part of the streaming into the thread that is closer to the hardware, which allows that thread to run unimpeded from the application thread and hopefully get you better performance.
Yeah, I had the distinct pleasure of working with UHD 4.0 with some of the apps engineers. We have a nice, if anyone's watching this, we have a nice demo of that running at full rate on an N310 in our kind of virtual demo booth in a video. So I encourage people to go check that out. That's some of your work, getting to be in a video studio. So I know that because that wideband streaming has been a big request, but other people, like last year, I know we talked about the data plane development kit. Michael, you worked on some of that as well, right? The DPDK aspects in testing.
Yeah, I was a little involved with some of the testing. I admittedly, other members of the team did most of the testing, the actual testing, but yeah, DPDK has really given us a boost to get to the streaming performance numbers that we've been looking for a long time, actually. And we had to gain some experience with DPDK because it is a very low-level thing. It's down at the kernel level, and even the hardware configuration can have an impact on DPDK. But once we got that nice and stable, we got some really good performance numbers out of a lot of our devices, especially the ones with the higher bandwidths. Looking at the X300, N310, and N320 devices, we were able to push those pretty much to full rate on all channels, and that was very exciting to get there.
Yeah, I always think it's like we enable all this great streaming. It's like the old adage, you can't hook a fire hose to a garden hose type of thing. So, I think some of those improvements that Ciro is talking about on the host side make that possible, that for pulling that data, consuming it, and doing something meaningful with it on the host, is probably more possible now than ever, without having to have like a monster supercomputer. Probably need some pretty powerful computing on the host side. So I guess, are there any other points that you wanted to make about some of the streaming enhancements, Ciro? I wanted to ask Michael a few questions about the test framework, actually.
I think I covered most of it. One thing that I remembered, we added a way when you have multiple network interfaces. Previously, UHD would assign for you what the interface, what channel goes through each interface. And you didn't have much control over that. So in UHD 4.0, we still do that, but we have a way for you to select what interface to use for each channel. So if you have one streaming path that is slower than another, or if you have multiple streaming channels and you have a few that are slow, you can combine them into one interface and have the higher bandwidth channels going through a dedicated interface. So that you can balance your streaming better.
Yeah, we had to do that on that demo video that's in our booth, and it was a dual 10 gigabit Ethernet path, and I believe we used that feature where you can kind of connect multiple streams together. So no, that's cool. Thanks for sharing. So I mean, I guess the last topic I wanted to highlight is Michael West. Everyone in the community, if you don't know Michael West, you will know Michael West. You've been with Ettus Research for how long, Mr. West?
7 years now, working on USERPs, and it's been a great ride.
Yeah, well, it's like we actually, I wrote a blog for the conference, and I was talking about how the GNU Radio Conference is 10 years. Ettus Research with NI is 10 years this year, so it's kind of a neat thing. You've been here for most of that.
Yep.
As part of the SDR team. So, appreciate all your hard work. And this in UHD 4.0 was, this is open source. And I think open source kind of forces us as software engineers to keep the code clean, because people are going to see under the hood. You don't want to see any of the source code I wrote when I was in R&D. It wasn't very clean. But another really, really important thing is testing. And I think I was talking with you and some of the team members about some of the enhancements to testing to ensure it's, stable when it hits the repository. So can you talk through some of the body of work that you've been working
Yeah,
in that direction?
Quality has been definitely a key for us on UHD 4.0, and testing is definitely a key part of that. So, first, let me just go over the challenges we had to face. We had 831 commits to the code, major architectural changes, including RF NOC, including the streaming architectures. We moved to an embedded systems. We moved to the Zeus branch for open embedded. We have more devices than we've ever had before that we actually have to keep stable and have to keep functional. Between the N200 series, the B200 series, X300 series, E310, E320, N310, N320. We have so many devices. And we also decided to integrate the FPGA repo back into UHD. We are, at the same time, we're supporting now a multi-USERP API and an RF NOC API. And we're trying to support those on both C++ and Python. So amidst all these massive changes, we're still trying to maintain stability and quality. And despite all of those challenges, we were able to actually increase our overall test coverage to keep all of our platforms very stable. We've fixed many of the longstanding issues. You've mentioned all the streaming performance enhancements we've done. So we're able to stream at full rate on many of the devices. We made substantial changes on the TwinRx RF performance. So we've got rid of a lot of the RF noise on there. We had a spur at DC that we got rid of. We added a power calibration utility in this. And when the release finally does come out for 4.0, which should be very, very soon, if not by the time of GRCon, we're updating also the SDK for the B200 firmware and bootloader to bring that more up to date. So we've had a lot of challenges, but we've had a lot of wins. And I think that people are going to have a very good experience with 4.0 and the quality going forward.
Yeah, I was always, whenever I was in a software developer in R&D back 10 years ago, I was always impressed with those labs of automated test suites. It's the testing doesn't get as much glory, but whenever something doesn't work right, then you're upset that it wasn't tested right. So fortunately, we know a company that knows a little bit about software testing.
And obviously this is an open source community, and I just want to reiterate that the GNU Radio community has actually fed back in, and the things they've reported on the mailing list, the pull requests they've put up on our public repos, all of that stuff we have actually pulled in and incorporated into UHD 4.0. So the contribution from the community has made a big difference as well. So a big thanks to everybody in the community that has contributed.
Yeah, that's a great point. I'm lacking. I haven't put in any pull requests. So I appreciate everyone's time, and go ahead and mute there, Mike. Appreciate it. I was getting a little bit of an echo. So I'm excited that UHD 4.0. We're slotted to have it released by GRCon. So by the recording of this video, it should be released by then. It's about a week and a half away. And we're excited about seeing what y'all are going to do with the FPGA, with some of the streaming, and there's a number of other applications. There are going to be a number of chances throughout the week to connect with us. So come to our chat room in Matrix and reach out. We're happy to set up a meeting and sit down and talk through how we can help you with your wireless application. Just kind of connect with some of our expert. It's all hands on deck this week for us at Ettus Research and NI. We're excited to again be here at GNU Radio Conference, albeit virtually this year, and we look forward to the conversations this week and seeing you all again in person next year. Yeah, thank you for your time today. And thank you, gentlemen, for joining me.
Thank you.
Seth Heitfield is a research scientist in the Computational Sciences and Engineering Division at Oak Ridge National Laboratory. His research focus at ORNL includes software-defined infrastructures for science federations and energy systems and signal processing on high-performance heterogeneous embedded systems. Prior to joining ORNL, he earned his PhD and MS in computer engineering from Virginia Tech. His research focused on wireless communications security, where he developed architectures for secure software radios using a defense in-depth approach to protect system components from exploits. While at Virginia Tech, he also worked at the VT ground station and Space at VT on several CubeSat projects that are currently in orbit. Please welcome Seth Heitfield.
Hi, I'm Seth Heitfield, and today I will be giving an update on some of the GNU Radio work that our team at Oak Ridge National Lab has been doing for the DARPA DSOC program. Just a little background on myself before we begin. I recently joined the lab as a research scientist in the Computational Sciences and Engineering Division, and prior to that, I was finishing my PhD at Virginia Tech, where I was focusing on security for software-defined radios. Here's a quick outline of my talk today, and we're really going to focus on the programming systems and runtime systems work that we have been doing. We'll also talk some about the example target application of workflows that we have been using to demonstrate how some of this work can be integrated into the GNU Radio ecosystem. Over the past few years, we have seen a massive shift in computing towards extremely heterogeneous systems, and this trend will only continue to grow. We do see a lot of benefit from moving towards these systems in terms of high performance and reduced power consumption because we can offload the applications and workflows ill-suited for running on a CPU to hardware that is specifically designed for that application or for that purpose. For example, in the mobile computing world, many of the devices and functionalities of those devices, such as the wireless connectivity, video processing, some of these things have been offloaded to co-processors rather than executing on the main host, just in terms of better performance and better battery life. However, as things become more complex and more heterogeneous, there is this massive trade-off in terms of the software and infrastructure and the complexity of that in being able to fully utilize these devices. Here are some quick examples of some of the systems that we have been testing with as part of this work. These are all systems available through the Experimental Computing Lab at Oak Ridge. The Summit Node and the DGX workstation shown here are examples of the high-performance class and cloud computing class systems. And the Summit Node is an exact copy of the hardware that is actually used within the OLCF's Summit supercomputer. Another example of a heterogeneous system that we've been looking at, specifically for mobile computing, is the NVIDIA Xavier SoC. This system includes an octa-core ARM CPU, as well as a GPU, deep learning accelerator, a vision accelerator, and several other types of multimedia accelerators. The Qualcomm Snapdragon is also a similar system for mobile computing that is also very heterogeneous. One interesting feature of this processor is that the CPU cores themselves are even heterogeneous and use the ARM big little architecture. All of these example heterogeneous systems really raise the question of how do we best utilize these systems? These typically have multiple processors, multiple types of processors, different interconnects, and each of them likely have a different programming model, which there becomes a lot of complexity in how you best and how you efficiently use those resources. One of the big issues is that we see this productivity versus performance trade-off. Programmers and engineers are going to have a large cost in terms of getting up to speed with the different programming models, and that is going to reduce their overall productivity because these accelerators may be very different from a traditional CPU programming model. So the goal of our work is really to simplify this process of integrating these accelerators into these different applications. Are there ways of hiding these complexities so that the programmer doesn't need to be concerned about the specific programming models of an accelerator? And once we have hidden these complexities and we have codes targeted towards those accelerators, how do we efficiently and intelligently offload these onto different heterogeneous devices? We're really trying to look at this from a full development lifecycle. Given the applications, can we break these applications down using ontologies into understanding all of the different methods and computations that are occurring within those applications? And based on that, and targeting and looking at off-the-shelf hardware, how can we map those applications with a given programming system and a given runtime scheduler efficiently onto the hardware so that we can accelerate that application? As I mentioned before, one of the biggest issues with heterogeneous systems is understanding how to program the different accelerators and their given programming models. With our project, we're trying to help simplify this through the use of the OpenARC compiler and OpenACC. OpenACC is an open programming standard for accelerators that uses a directive-based approach. Now, this directive-based approach allows a programmer to provide hints to the compiler that allow the compiler to determine what parts of the code can be accelerated and how that code might be accelerated on a target device. And the benefit of this is it allows the programmer to do this without having to modify or adapt the code to target the device in question themselves. Our OpenARC compiler is a high-level intermediate representation compiler that uses OpenACC and provides source-to-source translation from the input OpenACC codes to the codes specific to a given accelerator. So, for example, there can be several target architectures such as NVIDIA or AMD GPUs, different FPGAs, and what OpenARC is able to do is take this original OpenACC code and then compile it to the proper source code that can be compiled by that device's given runtime. And this is very useful for studying different directive-based accelerator computing. So the high-level representation is easy to understand and transform the program input. And there are various passes that can be done in order to determine the best way to program for and best way to generate code for a given accelerator. This is an example of what this mapping strategy can look like. In this situation, we can have a singular OpenACC-based GNU Radio block that when passed to the OpenARC compiler, the compiler can actually output several different target source codes for whichever devices are available on the system. So in this case, you could take this original OpenACC block and generate a CUDA variant or an OpenMP variant for running on the CPU or an OpenCL variant for running on an FPGA or a GPU. This is an example of what an OpenACC GNU Radio block might look like. So in this case, we have a GRACC base class, which the block inherits from. And this allows us to do some things such as initialize different parts of the OpenACC backend and the runtime to make sure that thread safety is satisfied for accessing data within the block. Included here, we also have the reference CPU implementation, which is from the original GR blocks that may have already been vectorized. And we also have the OpenACC accelerated version. Now, there are some specific tasks that the OpenACC version does when executing, such as copying data from the input buffers to device memory, executing the kernel, and then copying data back. And when using OpenARC, this block gets translated to multiple different programming models based upon the devices that exist in the system. And again, the main entry function to the system would be the work function of GNU Radio and the GNU Radio block. So every time the work function is called by the scheduler, depending on the context, the OpenACC runtime can determine whether to execute on the CPU or whether to execute on the target device. Here's an example of the performance that we might get using OpenACC to accelerate a block such as the FIR filter block. So in this case, we ran this with a reasonable filter size tap of just 64 taps. And we have a offloaded GPU version. And this GPU version has to do memory transfers between both the CPU and the GPU. And it's interesting, and as we've seen before in the community, there's a trade-off where the GPU version might actually be slightly slower than the CPU version until a certain point where the buffer sizes are large enough that you actually gain performance by offloading the larger buffer sizes to the GPU when doing this execution. So at this point, as long as the input buffer size is greater than about 2048 samples, the OpenACC version will outperform the original CPU version. Until that time, the CPU version can actually outperform the ACC version just due to the overhead of the memory transfer and the kernel launches. After we use OpenARC to generate these different output blocks for given target devices based upon our OpenACC input block, the next step is being able to intelligently determine where and on which accelerators these modules should run in order to gain the best performance. And this is where our Iris intelligent runtime system comes in. The goal of the Iris runtime system is to provide programmers a unified task-based environment that allows them to write portable code for multiple heterogeneous architectures. Currently, Iris is capable of running all the way from an embedded system on a chip, such as the NVIDIA Xavier, to leadership class supercomputers such as OLCF's Summit system. It gives you a graph-style task scheduling system where tasks are units of execution that can be scheduled for any specific device. There are different selection policies and scheduling policies that can be applied to these tasks, and it also provides you a shared virtual device memory so that there is memory consistency throughout the entire system. And we've also started integrating this with GNU Radio in order to be able to support GNU Radio running on these different heterogeneous systems. The Iris architecture can be characterized in these 4 ways. First, it executes as a single node system with the host CPUs and multiple connected devices. Now, these compute devices can be GPUs, FPGAs, and other accelerators, in any combination of those. It also uses a consistent memory model where there is a separate host space and the shared device memory space. And all of the devices, all of the connected compute systems share this memory space so that Iris can control memory consistency throughout an application's execution. The execution model is this task-based parallel execution where any of the individual tasks can be scheduled on any of the compute devices that are connected to the system. And finally, the programming model is through the OpenARC programming system. In that situation, we would have OpenACC blocks that can be then compiled, and the compiled blocks can be pulled into the Iris runtime for execution. It also has the lower level support where developer could write specific code to target a device of their choice. Task scheduling with Iris is handled with multiple in-order commands. So a task itself is a simple scheduling unit, and there are multiple commands such as the kernel launch command and memory commands that can be executed for each task, which handle moving device memory to the host or host memory to the device. Another key to take from this is that each task queue can have a specific device selection policy. Some of those policies include a developer requesting execution on a specific device type, such as a GPU or an FPGA, or you can specify things such as ontology or locality-aware device policies. And the Iris runtime will then choose the proper device to execute based upon, for example, a given ontology of an application or where the data dependencies exist and on which devices that data is valid for. Iris's memory model allows it to handle memory consistency while executing a specific application. What this simply means is that if there is a data dependency between 2 tasks, and a programmer has set a policy for executing one task on a specific device, the runtime will automatically determine that a memory movement needs to occur between the two devices and will trigger this memory movement before executing the next task in question. So for example, on the right, task 0 may be executing on the NVIDIA GPU, and task 1 would be executing on an ARM CPU, but the Iris runtime understands and can automatically transfer memory from the GPU to the CPU before executing task 1. Another interesting aspect of the Iris device selection policy is the locality aware. Now, very similar to the memory consistency model, this in turn allows Iris to specifically pick a device for executing a task based upon where memory was last used within the system. So in this situation, the data from task 0 is the dependency for task 1, and because this data already exists on the NVIDIA GPU device, Iris will already schedule task 1 to also execute on the GPU to maintain the locality of that data and not require a memory transfer. The last main focus of our work for this program is understanding end-to-end SDR applications that can make use of our programming and runtime systems to execute on these heterogeneous systems. One of our goals in choosing specific end-to-end applications is to really demonstrate the entire framework, including the programming systems for OpenArc and the Iris Intelligent Scheduler, running for a real-life SDR application on an example heterogeneous system of interest. And when choosing these, we need to make sure that the applications we choose are scalable, because we want to be able to execute these on embedded systems all the way to leadership class computing systems, and that these systems are easy to understand from an implementation perspective and easy to verify to make sure that everything is running successfully. To that end, we've chosen really a signal detection, classification, and processing example to really draw out these benefits. Mainly, we're focusing on multi-channel broadcast FM. The FM signal, the analog FM signal, is not a very complex signal. However, it gives us a very large amount of parallelism in the number of channels that we can begin to process. So for example, there are 101 total different channels. Each of those channels can have multiple types of output. You can have the mono signal, the stereo signal, the radio data service signal, and even HD radio. And each of these signals becomes more complex for each of these outputs. So there's a lot of simultaneous demodulation and simultaneous processing that we can do for each of these channels. And it's very flexible because we can scale the number of demodulated channels based upon available resources. The larger the system, the more channels we can process. And it's also flexible in the sense that we can demonstrate processing different outputs. And each of these, as I said before, each of these outputs becomes more complex. So it gives us a lot of flexibility in how we can set up our system. For example, we can use a lot of dynamic behaviors. We can look at detecting the active channels and only allocating resources to demodulate those channels at runtime. And then we are not wasting resources on inactive channels. We can also switch the active output based upon the signal environment. So for example, we could process the high definition signal if the signal to noise ratio is high enough. And if it is not, we could drop back to either the stereo or even the mono signal. So this gives us a lot of dynamics in how we can design this application and a lot of flexibility in how it can be implemented. And in the future, we can even look more at doing machine learning for signal detection, using direction finding with MIMO input. So there's a lot of flexibility in how this end user application can execute. So really quickly, here is an example of our transmitter flow graph. And this is just the simple mono signal So in this case, we have multiple channels that are being piped in, and this allows us to generate synthetic input. So that's another aspect of the system, is that we can very easily generate synthetic data that can be used for our demodulation step. And this is just an example of our receiver flow graph. And the goal here is to really process as many channels simultaneously as possible. That way we're making full use of the accelerators, and that we're trying to utilize the resources available on our heterogeneous system as much as possible. So based on this, we have been able to start replacing different blocks within this flow graph with OpenACC accelerated blocks. Now we're mainly focusing on integrating just the mono signals right now. But going forward, we'll be increasing this to include the stereo, the radio data service, and the OFDM-based high definition radio signals as well. But as we started integrating these OpenACC GR blocks into the system, this started showing several integration issues, mainly resulting to resulting to buffering. So for example, handling buffer management within an accelerator can be very difficult. And this goes back to some of the work that I've previously done with custom buffers, which we'll talk about in a second. But in this situation with the GNU Radio runtime, memory for each of the buffers is allocated by the runtime. However, buffers for accessing a specific device might need to be allocated through the framework. So for example, for an NVIDIA CUDA device, through the CUDA runtime. So this increases and causes this double copy problem between the GNU Radio buffers and the buffer for the given accelerator. And this double copy problem can definitely cause a lot of performance overhead within the system. So for example, the basic memory management that we can do for an OpenACC enabled block is when each block's work function is executed, we can then copy device memory from the GNU Radio block to the device. And then of course, we'll have to copy it from the device back to the GNU Radio buffer. And then for a second block, we'd have to do the same thing. So this incurs an additional copy between the device memory and the host memory just to go between two sequential blocks in a flow graph. This can be optimized in a situation where both blocks exist on the same device. That memory copy between the device memory and the host memory can be removed, and then the devices can just pass data through between each other as long as they're on the same device. However, this still doesn't solve the issue that there needs to be an initial double copy to get the data from the GNU Radio flow graph to the device kernels and to the device before each of these kernels can execute. Like I said before, this is really what is a motivating factor for some of the existing work that I've worked on at Virginia Tech. So one of my roles is pulling these custom buffers and integrating these custom buffers that I previously worked on into some of our demonstrations and examples to show the benefit of how this can remove the the double copy in the system. So in this situation, this requires some changes to the GNU Radio runtime, which allow the blocks themselves to tell the runtime that they need to allocate and own their own buffers. So these buffers can be created by the blocks, and then a buffer pointer is passed back to the runtime. And then the runtime at that point can manage the samples and the pointers that are going through each of these circular buffers. And in some cases, this also brings up the issue of memory mapping with the doubly mapped memory buffers. So that's something that the scheduler needs to guarantee that the memory pointers are valid when calling an accelerator function. So that is something that has to be considered when building these buffers. The advantage of having GNU Radio's custom buffers, again, allows the blocks to allocate their own specialized buffers, which means that, for example, using NVIDIA, you could use the NVIDIA runtime to allocate the CUDA buffers, and then the GNU Radio runtime can write from the previous outputs in the previous block output, can write directly into those buffers, thus removing the need for the double copy from a GNU Radio buffer to a accelerator's runtime buffer. One of the goals of this project at Oak Ridge is to really integrate with the GNU Radio community and collaborate and hopefully bring some of this work and experience that we've had on this project back to the GNU Radio ecosystem. So this includes doing things like working with other performers in order to integrate the ideas of custom buffers into the GNU Radio runtime so that it can be beneficial to all kinds of different accelerators. Also, that includes the ideas of block portability and concepts we learned from there and how to best target GNU Radio blocks to other accelerators very simply. And lastly, being able to integrate some of the concepts from the iris scheduling and the different things we've learned there into the future GNU Radio schedulers and runtime. So in summary, we talked about OpenArc, which is our programming system that uses a directive-based high-level programming model that allows for seamless porting of applications across different heterogeneous devices. And this really simplifies the workflow of being able to include different accelerators into a flow graph when you write GNU Radio blocks using OpenACC. The intelligent runtime system, Iris, provides us this unified task-based environment so that we can write code that is portable across multiple heterogeneous systems. We also have our end-to-end example multi-channel simultaneous FM receive. Now this gives us a very simple flow graph that is both flexible in the configurations that we can use and the outputs that we can demodulate, as well as a scalable flow graph in the sense that we can scale it to many, many channels at a single time. So that can really demonstrate the benefits of using things such as the OpenArc compiler and the Iris runtime component on these extremely heterogeneous systems. And last, our goal is to really integrate this work that we're doing at Oak Ridge into the GNU Radio community through things like the custom buffers work and taking lessons we've learned from the OpenArc and Iris programming system and runtime systems and applying that to the future GNU Radio runtimes and schedulers.
Hi, so that's the end of our conference today. Thanks to all of our speakers. GNU Radio Conference, of course, couldn't happen without all of the presenters who contribute their time and experience for this. I've been told to wrap up quickly so that we end on time, so I will do that. I wanted to particularly highlight Daniel Estevez and Wiley Standage-Beyer, who gave workshops today. They did a great job, and I've been getting some great feedback about those sessions. Tomorrow, there's 2 workshops. There's Python for the Rest of Us by Mark Thorin, and the FPGA development using USRPs and the RFNOC framework by Neil Pandya and Jonathan Pendulum. I've been told that neither of those have advanced homework, so do take the night off and rest. If you're in those workshops, you'll be receiving info about joining those very shortly. The other note is that we did have a whole bunch of no-shows to workshops, so if you're in the wait list, you may be getting an email as well this evening saying that we're letting some folks in. We start again at 10 a.m., same Eastern Daylight Time, not Eastern Standard, Eastern Daylight Time. And I hope folks will be back then. Chat system will be running smoothly. Michelle Thompson, the chair of the conference, has a brief announcement about the Capture the Flag, and I'll hand it over to her, and then that'll be us for the evening. Thanks very much, and see you tomorrow.
Greetings. My name is Michelle Thompson, also known as Abraxas 3D. I'm a co-chair of GNU Radio Conference 2020, and I organized the CTF this year. Here's an update. Team Platypus Aerospace and Argilo are tied for first place at 135 points each. We have 49 on the board and 70 registered. Please check out the CTF, come to the CTF room, and you'll find the server in the room topic. If you need help, just ask. Thank you so much and good luck.